So we wanted to begin today by thanking everyone for joining us. We're really excited by the number of participants who have chosen to join us for the first summit on drone geophysics, hopefully the first of many. Today is, as you all know, the second day with a heavy focus on magnetics. We have a handful of fantastic speakers who will go over, as far as I can tell, pretty much every area of drone-related magnetics that they can. In addition to thanking all of our participants and the presenters we have today, I wanted to thank our sponsors and SEG for their participation. Lori, would you pull up the sponsor page for me?
Sure. You have perfect timing. Voila, there it is.
We've been extremely fortunate to have 5 companies to sponsor us. You'll see that they just went across the screen. Lori, I can't actually get my program booklet open, so if you wouldn't mind checking or reading those off for me. We wanted to just get a couple of housekeeping things out of the way right at the beginning as well. For those who joined us yesterday, you remember that we asked that all questions be placed in the Q&A box at the bottom as opposed to the chat box. The reason for this is that all questions recorded through Q&A, we will then be able to save both the questions and the answers and include that in the documentation that can be shared afterwards. This event is being recorded, and for those who have chosen to participate, you will have access to the recording. Not immediately. I don't know if those of you are familiar with how this process works, but it can take a little while to get the videos edited and prepared to share. So expect an email probably in a few weeks. So you will have access to this again later on. I also wanted to emphasize that part of the goal of this particular event is to really allow for networking and creation of collaborations between different participants. So if you see something that someone is working on that's relevant to you or that you'd like to learn more about, don't be afraid to reach out to them either through the chat or as you've seen on the screen, we are sharing the contact information of all of our presenters. So, and then sorry, did someone want to add something?
No.
No, I was moving my chair. I apologize.
Okay. I also wanted to add that during the course of these presentations, we have so many wonderful presenters that we're going to be a little tight on time. And the result of that is don't stress out if we don't have the ability to get to your question immediately during that talk. Just like yesterday, there will be a discussion portion at the end where we can continue to address any outstanding questions or have a dialogue. So don't worry, all of your questions will hopefully get answered, even if it's not immediately following the talk that it's relevant to. And on that same note, similar to yesterday, please include the name of the presenter you are addressing with your question. As we mentioned, there's enough presenters today that it will become a little confusing at times if you're addressing someone other than the current presenter. So it just helps for housekeeping if you include the name of the presenter you're addressing in your question. Beyond that, we also want to make sure that we kind of emphasize that as this is the first of its kind, the first event of its kind, Ron and I and Lori have already begun discussing what the future looks like. We intend to have an additional summit on drone geophysics this coming, next fall, so fall 2021. And we are looking for a panel to join us in helping organizing this. So if you're interested in really pushing this to the next level, please reach out to the Near Surface SEG and let us know that you'd like to participate. We've already received a couple of people or heard from a couple of people that they'd like to participate. And on that same note, we just want to thank SEG and the Near Surface Technical Section for their support and making this event possible. This is kind of the beginning of a new chapter for Near Surface, as we'd like to organize similar events in the future. So Ron, I apologize, I'm a little scatterbrained this morning since my computer's not working quite right. Did I miss anything?
No, you hit all the nails right on their head. So you did a great job, Morgan.
Wonderful. Well then, without further ado, I'm going to have Ron introduce our first speaker, and we'll get to it.
All right, thank you. The first speaker is Irina Arena. Hopefully I've not mispronounced that, Irina. From the University of Nebraska. The title of her presentation is Testing a Low-Cost Drone-Based Magnetic System. Take it away, Irina.
Hello, thank you so much, Ron, for introduction. Hello, everyone. My name is Irina Arena. I am assistant professor at the University of Nebraska at Lincoln, and I am presenting this talk today on behalf of my student, my undergraduate student who just graduated in spring 2020. And this project was the core of his senior thesis, and it was focused on assembling and testing a low-cost drone-based magnetic surveying system. Here's an outline of my talk. I will touch on introduction and motivation, what we were thinking about while we started that project, what components we have for our system, the study area where we tested. We did only one test service up to now because it was affected by COVID pandemic. I will show you our results, and the way forward, as I already mentioned, it is affected by the pandemic. So what we wanted to do is to come up with a system that allows us to collect safely magnetic data over some areas that we are not, we do not want to walk. For example, like cornfields of Nebraska, right? We wanted to collect the data, and that's not always feasible to walk over those cornfields. So we decided to come up with that magnetic system. We started the project in spring 2019, a year ago. Not a year ago, spring 2019, and that was a year-long project for a student. We started with evaluating different drones, and we arrived to the same conclusion that Kian and Krista showed yesterday, that they use Matrice 600 Pro drone from DJI, and that's what we decided to use as a carrier for our NV Mag Pro sensor. We have assembled our system in spring 2019. We collected a series of tests on ground-based tests. So we were walking, we were running with the sensor, we were looking for different parameters, how far away the sensor should be from the drone, and so on and so forth. But then in fall 2019, I attended SCG convention, and I actually attended Ron's talk about his experiments with Mag-Arrow instrument. And that Mag-Arrow instrument was kind of our inspiration for our system. We understand, we realize that our system is obviously less sophisticated and much more simple than Mag-Arrow, but that actually allows us to keep the phrase low cost in the title of this talk. So here is our system. We have that Matrice 600 Pro, that's a carrier. We have a sensor, we have 2 meters cable, and that's our sensor. From the very beginning, I want to state that our sensor is a proton sensor that must be oriented to the north. So there is one step in our workflow right after the takeoff. We have to make sure that the sensor is oriented to the north. That is something that Mag-Arrow doesn't need to bother because they do not need to be oriented. That's one of the discrepancies between us and Mag-Arrow. Here is our magnetometer. The entire system is here. That's a span for a scale. The total weight of that console and the sensor is 3.4 kilograms, which is easily can be carried by our Matrice 600 Pro for about 20 minutes. So we had to wrap our sensor with approximately 1 inch thick foam to protect it from potential damaging during landing. We had to mark the north with the red tape so that it could be visible during surveying. Here is a console. We attach the console with carabiners to the frame of the drone, and we actually had to use a little bit of rope to extend that a little bit in order to make sure that we can put our hand in to operate the system. So again, it may not look fancy. It is cheap, it's safe, and it does the job. So that's a chart about our drone. Depending on the payload, that is the flight time, and it also depends on the type of battery. We purchased 2 sets of slightly sophisticated batteries, so that is our estimated flight time, up to approximately 20 minutes. I would like to stress that our drone is capable of flying with 18 meters per second. That is way too fast for us. We do not have a capability to record that data at such a speed. So again, that's another discrepancy between us and Mag-Arrow. Mag-Arrow probably capable of recording in such velocities. We are not using our drone to that capability of fast flying. Here is the first after measuring the noise from the drone to the sensor. And here we see the graph with his measurements. And after 70 centimeters, the noise level is steady. So basically that suggests that the minimal cable length between our sensor and the drone should be 70 centimeters. In reality, we use 2 meters. And this is because we want to protect our sensor during landing from possible potential damage, because during surveying, the sensor lands first, it touches the ground, and then the operator manually moves the drone away from the sensor, and that's why we prefer the longer cable just to keep the sensor safe. Here is our system. Before starting the survey, the operator starts magnetic data acquisition like this. Right after the takeoff, you can see in the center figure here, there is a little bit of swaying, a little bit of swinging of the sensor. That is because of the sudden motion of the drone. And that swaying also occurs at takeoff. It also occurs at every time when the drone makes turn. So we have to do something to accommodate for that, to take it into account. And we actually arrived to the same conclusion that Alexei Dobrovolsky mentioned yesterday during the discussion. So we design our profiles to be longer, our flights to be longer than our actual profile. So the drone should approach to the first starting point already at constant speed and with swaying already settled down. When it's surveying, it's actually not that bad. For whatever reason, my cursor is not working. Just bear with me for a second. I'm trying to run the video here, which is not working. Okay, I will continue and maybe we'll figure out what's going on later. Here is the information about our test survey. The study area is approximately 50 miles away from Lincoln, which is very convenient to us. We have a really convenient geologic object, mid-continent drift, right nearby. The fault that we did our survey over was north-bounding fault right here. That fault is associated with a contrast between igneous rocks and sedimentary rocks, so it's a huge magnetic anomaly over it. That is a known fault, but it's not exposed at the surface, so we used published maps to navigate our survey over that fault. So here is a cross section over that system, the mid-continent drift system, and this is the fault that we were surveying. Again, the fault originated more than 1 billion years ago as a normal fault, and during continental rifting, enormous amount of igneous materials was in place during that time. Then the rifting failed, and then the fault was reactivated as a thrust fault, and all of that material is now brought higher in the section, and that is a contrast between igneous magnetic rocks and less magnetic Paleozoic sediments, that's what causing our magnetic anomaly. The test area is over the cornfield. The cornfield is owned by Lehman Ritchie Corporation, and we are extremely grateful to them for allowing us to access that field. The corporation lends that field to the farmers, and we had to wait until farmers pick up the crop before they allow us on the field for surveying. So the study area we were given was 200 meters by 200 meters square right here. That is a published fold. We have designed 2 flights, as we have 2 sets of batteries. So the 2 flights, one was the red line here was 12.5 minutes, because that was our first flight with that system, and we didn't know how well it will go, how long we can fly. The second one, the blue one, is slightly longer, 18 minutes, and all of that was relatively fast and easy to do. The methodology is that the operator manually takes off the drone, then the drone starts following the programmed flight pattern. What we also done is to add those 10 seconds pauses at each waypoint, and that was done intentionally to allow swinging to settle down. What I can comment that the 10 seconds probably is a little bit too much. Next time we probably will limit that to 5 seconds. So that is enough for our swinging of the sensor to settle down. This is another illustration of another huge disadvantage of our system with respect to Mag-Arrow. Our sensor doesn't have GPS. I think Konyan mentioned that yesterday in the discussion as well, that we have to merge, similarly to him, we have to merge the GPS data with our sensor data, and we use the timestamp for that. And that again mandates another step in our workflow. Before the survey, we have to make sure that the timestamps on the drone and on the sensor are the same. Here is the resultant map. Just a disclaimer for Elizabeth and Lauren. We do have a license to OASIS montage. This map is done in ArcGIS because the student used this data set for ArcGIS class as well. So all of the analysis and the twigging and everything was done in ArcGIS. So here is our magnetic anomaly map, and the magnetic field changes approximately 30 nanotesla within the area. That is a published fold. It's slightly different from our interpretation, as you will see later. We also did some cross-point analysis in between those 2 flights, but I want to stress that many of our points are at the very corners, that they are affected by the swinging at the end of the profile, at the beginning of the profile. So we have 21 points, and out of those 21 points, we have one obvious outlier. If we keep the outlier, the average difference is 2.1 nanotesla. If we throw away outlier, is 1.9 nanotesla. So approximately 2 nanotesla difference. But keep in mind that many of our crossing points are toward to the beginning of the line. So there is obviously increased noise there. We also compared our data with published USGS map, and USGS map is airborne data. The grid is published with 500 meters intervals. There is luckily 1 point in our survey area, and we compared the data in that point, and we have approximately 30 nanotesla difference. The flights were obviously at different elevations. So the USGS flight is airborne. USGS data set is airborne data set. We were flying very close to the ground. We also didn't take into account any diurnal variations or anything. We just didn't bother with that. So we account that 30 nanotesla difference for diurnal variations and difference in elevations. So here is our map. So I just want to toggle in between. We can see that we have the same gradient as USGS. We also have slightly different interpretation for the fold in this particular block. However, we were not able to investigate further because we wanted to come back to the adjacent block, but then it was really rainy weather. We didn't feel comfortable flying at that weather. And then it was cold, and then it was spring, and then it was COVID. And now our project is on pause for, we are waiting for university to remove the ban on fieldworks, which probably not going to happen, at least this fall. Okay, so what we wanted to do, we want to come back there and do a walking survey and compare walking survey with the flight data. And we also wanted to extend to adjacent block just to see how the fault is behaving there. And the student graduated, so now looking for another student. Okay, here is the summary. Our system works. Yes, it is not as sophisticated as a Mag Arrow, but it does a job. We do collect reliable magnetic data. We concluded the following acquisition parameters as optimal after our single survey. So we fly at 7 meter elevation, so the sensor is 2 meters beneath the drone, so that's 5 meters above the ground. The flight speed is 2 meters per second. That would work better for us, and sampling every 2 seconds. So we also came up with a longer flight to avoid the noise, those longer flight lights to make sure that the swinging is taken into account at the beginning of the profile. And those pauses at each waypoint that they also help to eliminate noise due to swinging of the sensor. Here are our references. And if you have any questions, please ask me now, or you can reach me or the student with these emails. Thank you.
Thank you, Irina. We have a couple questions for you.
Yes.
So the first question is, the Z flight pattern is due to the fact that you have to maintain the orientation of the sensor, correct?
Z flight? No, we had to stay within our 200 by 200 box. That's all it was. We had to be within the box, and we wanted to use that as 18 minutes flight to cover as much as possible. So we designed 2 flights. One is perpendicular to the structure and one is parallel to the structure. But they all were in that Z pattern.
Wonderful. All right, then the next question is, did you observe a benefit for flying a sawtooth pattern as opposed to conventional lawnmower pattern? I guess it's a similar question to the one we just answered.
Yeah, again, this was our first survey. So we, for example, right here, right, if I design a profile, I didn't want to sample here because we wanted to cross the structure as much as possible. That's why we came up with that zigzagging pattern.
Next question is, how much error would you estimate in your magnetometer orientation? You said you had to orient it to the south. Could that account for the difference in your fault trace from other published data?
No, I don't think so. First of all, we oriented that to the north from the very beginning, and it's relatively easy to do with the drone. So with the drone just turns and the sensor turns and it's oriented. We kept an eye on it during both flights, so to make sure that it was always facing north. So I do not think that there is error due to improper orientation.
There's another question asking about how you correlated the magnetometer data with the drone position. I'm wondering if maybe that would be better answered.
I think I had a slide about that. Here we go. So in magnetometer, we do have a timestamp and magnetic reading. In the drone, we have a timestamp and latitude and longitude. That is what is downloaded from the drone. The drone is outputting data with 10 Hertz frequency. As we learned yesterday from the discussion, that's actually interpolation between 1 Hertz data from the satellite. So we just use the timestamp to merge the data together. Just a simple MATLAB code to blend them together based on the time.
All right. Thank you. I think we have time for maybe one or two more questions, and then there are more than that in the chat. So Irina, if you would be willing to answer the remaining ones in the chat after, that would be very appreciated. So the next, there's a number of questions regarding vegetation and the challenges facing that. So the question is, my question is, if the land is clear, the drone can fly with a small land clearance, everything is all right. However, if we have, for instance, woods or jungle, the drone must fly much higher and we miss some anomalies with small wavelengths. So do you recommend to diffuse the drone measured data with some land measured data, or perhaps it's not possible to use longer cables?
If there is a vegetation, the longer cables will probably make you more problems because first of all, you don't want to touch that vegetation. That's first thing. The second is the swaying of the longer cable probably will be more dramatic. You don't want that. And if there is a vegetation, I don't know if a ground survey will be better if I mean, if it's just trees, you probably can go around it. But if those are bushes or something, you don't want to walk on. It's better to fly. We may want to, you obviously may want to go higher, right? But you maybe want to go slightly slower over those regions to sample a little bit. Better to have more samples, if that makes sense. That's what I would at least try.
In that same vein, could you address whether or not the height of the vegetation really plays into the quality of the data?
I'm not sure because we didn't fly above any trees. Our spot was completely open. I think I had a slide. It was completely open, so we didn't touch anything, and the farmers didn't let us in before they collect the crop. So in our case, it was nice, easy, flat, and free of vegetation.
Wonderful. Well, thank you very much for your presentation, Irina.
Thank you.
Some of these questions are more generalized, so if any of our other presenters would like to also address them when it's their turn, it might be nice to get a bit of a perspective on some of the more general questions from our panel of presenters.
Thank you.
Thank you. All right, our next presenter today is, Ed Konyan. Ed, I hope I said your last name right.
Yeah, Konyan.
Konyan.
Yep.
And he will be presenting for us today on a comparison of flight height controlled UAV and ground vector magnetometry survey data covering an urban landfill.
Yeah, that's right.
And your affiliation is with the Red Rocks Geophysical Consulting, correct?
That's right, yeah. I hope you can hear.
Good morning, everyone. I'd like to thank the organizers for inviting me to present at the Drone Summit. That would be Laurie, Ron, and Morgan. And the title of this talk today is Comparison of Flight Height Controlled UAV and Ground Vector Magnetometer Survey Data Covering an Urban Landfill. Today we'll have a look at some calibrated and corrected vector TMI and compare a ground survey gridded data set versus a UAV survey gridded data set. And also at the end of the talk, have a look at a comparison with a high resolution alkali vapor magnetometer. The landfill is located in Golden, Colorado, and there was some previous work done here in 2018, which you can see on the left here with a scalar magnetometer. Here's the zoom in on the area. On the left, you can see the flight lines. There's 36 flight lines, about 15 line kilometers in total. And underneath, there's a TMI image that was done, the continuation filter 2 meters. That's UAV TMI. On the right, you see how noisy it is in this area. There's a lot of electromagnetic interference coming from major power lines. In yellow here, 230 kilovolts. Along the roads, there's 600 volt power lines. There's an amusement park that there was up on the hill here above the landfill. The town of Golden, South Golden's over here, and there's a rail station on the right here. So this is a noisy urban area to survey in. The equipment used for surveying is seen on this slide. On the left, we see the UAV and the flux gate vector magnetometer, or FVM. It's a Matrice 200 UAV with a camera, so you can record video or ortho photos while you're flying the mag survey.
Hello.
Data loggers connected there on the drone, and the sensors there in the front. On the right, you can see the ground magnetometer setups. On the backpack, the FBM is mounted here, and on the left, it's the alkali vapor benchmark that's used to compare the flux gate TMI data at the end of this talk. The specifications for both systems can be seen in this table here. They're both high-resolution magnetometers. The alkali vapor is expected as much higher resolution, but in a real-world surveying situation, we want to compare here what a picotesla resolution vector magnetometer TMI data looks like compared to the alkali vapor magnetometer. Prior to flying the FDM, full throttle noise tests were done on the ground to see how far away we have to sling the sensor from the flying UAV, and we came up with distances of 2.58 meters maximum. That's for the rear motors. So we mounted the slung the sensor 3 to 3.5 meters below the UAV. For most flying, it's probably 3.5 meters below the UAV, and we tried to maintain a 3-meter terrain clearance between the sensor and the ground surface. This slide here just shows some links to the equipment manufacturers and also to the LiDAR DEM provider, which is the USGS. This also lists some DJI system developer kit-based third-party softwares that can be used to fly the UAV. I tried 3 of these, but there's a selection there that can be tried. Okay, the LiDAR 1-meter DEM is used as a drake surface to control the UAV flight. The default drake surface in DJI is a SRTM, which is rate force. So this 1-meter resolution is actually higher resolution than the GNSS accuracy of the DJI Matrice GNSS system. You see the image on the left here. The arrows point out ridges that are about ankle height, maybe a bit higher between the ankle and knee, so it's high resolution. First step is to fly dummy flights, just to adjust the altitude with the software is used to get the clearance right at about a 3-meter average clearance for surveying. After the dummy flights, the sensor and magnetometer was flown over the landfill. Vector magnetometers have to be calibrated, corrected, and compensated to produce the highest accuracy TMI data. There are 2 main mathematical camps that study this. The first is the airborne Servo camp, which includes Poles and Lawson in 1950 and Leliak in 1961, where they studied the use of flux-gate vector magnetometers to compensate proton magnetometers or alkali vapor magnetometers. Second camp is the satellite magnetometry camp, which includes Grace Waba. He's the first reference I could find that goes back to 1965. And these rocket scientists use their vector tensiometer to study the attitudes of satellites in orbit. Munshi and his students, starting in 2007, showed that the satellite magnetometry equations were equivalent to Leliak's equations. And these simpler to understand vector tensor math formulations could be used to do the same thing as the Leliak compensation model, which is correct for hard and soft iron and eddy noise in vector TMI data. So this vector tensor TMI formulation is used to correct the vector data collected during this landfill study. So the vector tensor formulation can be used to do a figure of merit, just like the Leliak equation. Figure of merits are flown to calibrate the flux gate before correction and compensation of the platform noise. figures of merit approximate a lab calibration through a volume of magnetic airspace that is uniform throughout, or at least in theory. Always noise of some kind in the magnetic volume, as would be expected, and the practice is for, in the past, is to filter that out before you do compensation. In essence, what a figure of merit tries to do in the air is a lab calibration, which is shown in apparatuses here on the right, where a flux gate is rotated through 360 degrees on all axes, the X, Y, and Z. And that lab calibration is represented by this spheroid here in the center of the Cloverleaf or the box. You can fly a box at altitude or a Cloverleaf and try to compensate your aircraft. Now, traditionally, you fly roll, pitch, and yaws of 10 degrees, 5 degrees, and 5 degrees on an airplane, let's say a fixed wing, because that's what reasonably can be done at altitude. You can't, for example, using a helicopter here with a two boom mounted sensors, you can't do a 360-degree aircraft barrel roll. But in theory, you could, because if the airspace is uniform magnetically, there'd be no gradients in any direction. Or alternatively, you can try and do a pivot in the fuselage of your helicopter, in this case, rotate around like that, but obviously you can't do that either. Well, lastly, you can try and rotate or pivot around your sensors on the wings, but again, that's not practical. What can easily be done, though, is the rotation of a mobile phone on your hand. Mobile phones have coarse 3-axis vector magnetometers inside of them. This image on the right shows the raw and corrected data prior and after calibration. The raw data plots up as a 3-dimensional zeppelin over here with huge hard iron oxides of 246 and 50 nanotesla. And this is calibrated and corrected to get the spheroid calculation, a much more accurate magnetometer, which is centered on the centroid. And the spherical shape indicates that the induced iron effects have been removed along with the eddies. Not that there'd be many eddies with a small phone like this, but there would be inducements for sure, and that's been corrected here. So you have a much more accurate magnetometer for measuring the US field now. So based on the mobile phone example, it's easy to calibrate a small flux gate sensor in the field through 360 degrees. What Red Rocks has done at the landfill has taken a lab calibration based on this apparatus from Petruka and Casper. Fabricate something similar to this, not exactly the same, it's actually quite different, but it does the same thing as this calibration table. That is, rotate the flux gate through 360 degrees on all axes, roll, pitch, and yaw. This is a full field calibration of roll, pitch, and yaw, not just 10 degrees, 5 degrees, and 5 degrees. In the result, which we'll discuss a bit later, seen up here on the left, this is the result of the field calibration at the landfill. You can see how spherical the raw data is, indicating a high accuracy flux gate to begin with. And you can see the compensated, actually the calibrated corrected result. I'd say compensated. When you fly an isolated slung sensor, there is no platform noise to compensate. There's no hard and soft iron or eddy magnetization to compensate for. In that case, what your calibration becomes is a correction only, a correction of the flux gate errors of manufacture, and also of maneuvers through 360 degrees in the Earth's field. And what effectively happens is the hard and soft iron and eddy terms of the mathematics drop out of the equation, leaving just the correction for the flux gate sensor itself. As the compensations drop out of the math, the calibration and correction defaults to an FOM, figure of merit. The calibration motions through 360 degrees are the FOM. So they're not a partial calibration, they're full calibration. So what's done is the calibration was done on a sandstone outcrop, which is about the same height as the central one that's flown over the landfill. And they should have similar gradient profiles. The landfill is going to be maybe alluvial material, not very magnetic, but what's magnetic is the actual junk inside the landfill. And since this was a high accuracy, low noise flux gate to begin with, the improvement ratio of your calibration is lower than, say, what we saw with the mobile phone.
Ed, can you turn the volume up on your computer?
This is a result of the UAV
Yeah, 1 second.
flux gate calibration over the landfill. On the left is the ellipsoid, which is not very elliptical.
Let me
These
just,
are the 3 landfill survey days.
Whoop.
White noise plots prior to calibration is generated by removing the thermal drift and diurnal warm-up period. The flux gate requires a warm-up period.
1 second here. I'll just start that back up. Okay. I think we were on this slide here, and we'll start from current slide and see what happens. Oh,
These are the 3 landfill survey.
let's go here. There. Okay.
So this is a result of the UAV
Thank you.
calibration over the landfill.
Okay.
On the left is the ellipsoid, which is not very elliptical. It looks more like a sphere, and that's because the flux gate is low noise to begin with. The RMS error on the raw data is 7.38 nanotesla when calibrated. After calibration correction, the corrected spheroid here is centered on the centroid, and the noise is reduced by a factor of 3.4. That's called the improvement ratio. So you go from 7.38 nanotesla on your raw RMS down to 2.16 nanotesla on your corrected RMS. And that's through the full spherical field figure of merit. On the right here, it shows the overlap between the raw and the calibrated, corrected flux gate data, and you can see, see that it's a good quality flux gate. These are the 3 landfill survey days. White noise plots prior to calibration is generated by removing the thermal drift and diurnals from a warm-up period. The flux gate requires a warm-up period of about 20 to 30 minutes prior to use. The gray profiles are the raw, unfiltered response, and this is mostly local 60 hertz power line noise. An easy way to remove this noise is low-pass filtering, and the results can be seen by the blue and red profiles superimposed on the gray profiles. This urban landfill data in a noisy environment has to be power line filtered. The 20 hertz low pass sensitivity results are seen on the rightmost column of the table below the profiles. And these, all except one, that's UAV day 3, meet the GSC's 10 picotesla sensitivity numbers. But simple QA/QC of that profile, just removing a few of the spikes seen there, reduces that noise down into the 10 picotesla, sub 10 picotesla range, as seen on that yellow row going across at the bottom. That's the QA/QC UAV day sensitivity. And that data also meets the GSC 4th difference standards. As fluxgate vector magnetometer data is spiky by nature, you have to low pass it, especially in urban areas, to get rid of that urban EMI noise in the data. These are the calibration profiles for the 3 days landfill surveying. The blue profiles are the raw data, the green profiles are the corrected data, and the red profiles are the 20 hertz low pass filtered data. The bottom profile set shows some de-spiking that was done to produce the yellow colored row at the bottom of the table below the profile image. The raw data result shows that this fluxgate is low noise to begin with. The calibrated RMS shows an improvement of 2 to 3 times on the noise levels with the RMS. After 20 hertz low pass filtering, all the noise levels are well below 2 nanotesla. As mentioned with the static data, you have to low pass this data because it's in a noisy urban environment. What's seen also is after minor QA, QC, the UAV data is below 2 nanotesla RMS, so it meets the GSC 2 nanotesla specification for a figure of merit. And as previously mentioned, the calibration motions through 360 degrees for a slung isolated sensor default to the FOM because there's no hard and soft iron compensations or eddy compensations required. This is a look at the ground gridded data sets. The upper 2 images are from the ground survey. The one in the center is the straight ground TMI without any filtering, and the one on the right is the ground TMI upward continued 1 meter. And that upward continuation approximates the average height of the UAV survey off the ground at 3 meters. The bottom images are the straight UAV TMI on the right. In the middle is that TMI downward continued 1 meter. And on the left, the bottom left, is that TMI downward continuation filtered 2 meters. The black arrow in all images points out a common dipole on the images. And it's seen on the bottom that that dipole has been attenuated on the UAV survey data. The attenuation is due to a high flight line. The flight line over that dipole was about, the sensor was about 6 meters off the ground, whereas the average sensor height across the whole survey was visually estimated to be 3 meters. So that extra 3 meters attenuates that signal there. Also, the UAV survey was flown at 4 meters per second, whereas the ground survey was walked at about 0.5 meter per second. So there's about an 8 times higher sample density for the ground survey. So the ground survey does retain a bit higher resolution. Overall, though, the UAV survey looks to be a good approximation of the ground survey. There's another attenuation of signal here up on this signature. You can see, and again, that was a battery swap line, and the UAV was at a different height that was higher. This last slide shows the AVM ground survey TMI in the upper left, the ground FVM 20 hertz sampled TMI in the upper middle to match the sample rate of the AVM data, and the FVM UAV survey data on the upper right, downward continued 1 meter. The bottom 2 grids are difference grids. The bottom central one is the ground FVM at 20 hertz minus the AVM data, and the one on the bottom right is the FVM ground data less the UAV data down 1 meter. The arrows on the upper images point out a dipole common to all images. Pretty much what can be seen is all images approximate each other quite well. The bottom center difference grid returns a random pattern indicating little obvious line noise in the AVM or the FVM ground data. The bottom right difference grid shows some subtle line noise caused by battery swaps where the reflight lines flew a few meters higher, 2 to 3 meters higher than the original lines that were swapped on. But all in all, though, the FVM data will approximate each other, both the ground and UAV survey, when downward continued, and both approximate the AVM ground survey well. Some conclusions then are the UAV survey approximates the ground FVM survey when the UAV data is downward continued 1 or 2 meters. The ground FVM survey approximates a ground AVM survey. Surveyor line wander on the ground surveys and GNSS positioning errors for all surveys cause the most differences seen between the mapped TMI signatures. Particularly when UAV flight lines are flown a bit high, you get signal attenuation and the TMI is attenuated also. Another conclusion is that a ground calibration and correction of an isolated slung sensor below a UAV is a valid way to calculate a slung sensor FOM. It appears mathematically valid as the compensation components drop out of the math equation. The isolated slung sensor below a UAV is in the same position out in the field as an isolated calibration station for the fluxgate. Lastly, the fluxgate data collected in an urban environment after low-pass filtering pretty much can meet GSC standards for airborne surveys. I'll wrap it up there and take any questions. Thanks very much.
Okay, I hope you could hear most of that talk. I'm sorry I was a bit low at the start.
So I think that a couple of people were struggling to hear parts of that, Ed. Is it all right if they reach out to you for clarification?
Yeah, they can, yes.
Wonderful. I know we have a couple questions, but we're also a bit tight on time. So I'm gonna just read one question and then if you could respond to the others in the chat.
Okay.
In the question and answer box, that would be very helpful.
All right.
So the question for you is, did you fly a Cloverleaf test with your system? And if so, how big is the error?
No, you don't fly a Cloverleaf. And the reason why I didn't fly a Cloverleaf is that's just not done in commercial surveying. And it doesn't make any sense because all the noise that's going to be in that Cloverleaf is going to be external to the fluxgate sensor. So what is done is you find, what I did, I found an outcrop about the same height as the flight height of the landfill. And that was a sandstone outcrop with a low gradient. And the fill should be pretty low gradient also. So the idea here is you do a full lab type calibration at the same height and the same gradient regime as the landfill. And that corrects the fluxgate sensor on the ground through a full calibration, 360 degrees on all axes. And then if you look at the math, because there's no hard and soft iron to compensate for, there's nothing to compensate. So you're just correcting the fluxgate for manufacturing errors. And also you're correcting the fluxgate for any position in the Earth's background magnetic field because it's a vector magnetometer. When you do that, the fluxgate becomes pretty much immune from directional bias because you've compensated the sensor itself for that. So flying a Cloverleaf for a slung sensor that's only going to introduce external noise into your calibration of the fluxgate doesn't make any sense really. You want to do it, for example, when they calibrate magnetometers in a lab somewhere, they don't do it on a moving platform going through the lab. Obviously, you do it on a fixed point, you do it on a centroid. So it doesn't really make sense. I don't think any commercial, you can't do it with a scalar magnetometer for sure. You can't, no one I know of does FOMs on slung sensors that are, tens of meters below a helicopter or a fixed wing airplane. So this other people who've been doing this type of fluxgate work in Europe have been doing these ground calibrations. So I'm following their lead. And if you look at the math, it makes more sense to do a calibration on an isolated slung sensor, sort of in the same environment without any external motion noise coming into your calibration.
So Johannes is with the Mobile Geophysical Technologies. This is Johannes B. Stoll, and he is going to be presenting his talk, MGT Drone Mag 5 UXO Detection System.
Good morning. Can you see my screen, my presentation?
No.
No. So.
All right, we can see it now.
Perfect.
Just slideshow mode and then you'll be good.
Currently, I'm in Scandinavia, in Norway, on a UAV-based airborne MAC survey. And we fly for a Canadian mining company. The size of the area is 12 square kilometers. And today it's our the third day. Unfortunately, we had to stop our flight operations at lunchtime because we experienced very gusty winds, so we had to stop. So the idea of Drone Mag 5, we call it Pentamag, was to develop a system that allows more or less 100% coverage. And in my talk today, I will show you the results we have collected on a military test site. I have 4 points. I would like to talk a little bit about the performance required by multicopters based on UXO detection. Then I would like to speak a little bit about the correction and the resolution of flux gate magnetometers. We already heard a lot of technical things from Konyan. Then I show you the results of we obtained on the military test facility. And finally, I show you an analysis and the resolution we have gathered during this test. The idea of using airborne MAC systems was created already more or less 20 years ago. And on the left panel, you see the OREX system, which was developed by Oak Ridge National Laboratory. It should provide more or less 100% coverage of an area and gather very spatially dense data. And secondly, it should allow for extremely cost-effective data acquisition in wide area. But as you can imagine, there is a strong risk for the pilot because the system is only effective if you fly very close over the ground, more or less 2 or 3 meters above ground. So the idea for the Pentamag system was to build a system that also allows to collect very dense data and also increase the production rate. Of course, we fly usually with an average speed of 4 to 5 meters per second. We don't have the same production rate like the OREX system, which can obtain 15 to 20 hectares per hour, whereas our production rate is only 2 hectares per hour. The performance we want to see is it should first reduce costs. It should allow 100% coverage. For a multicopter, it's very important that the power is very low. The power consumption of the system, a measuring system, is very low compared to the power ratings of the multicopter. It should allow RTK accuracy in the order of a few tens of centimeters or 10 centimeters. In order to fly very close over ground, we use a laser altimeter to achieve this low altitude. This is a key feature. If not, you immediately will use resolution. to be very flexible and cost effective. The UAV shouldn't exceed a maximum takeoff weight of 25 kilogram, which allows to transport it to almost any place on this planet. The sample rate should be more or less at least 100 hertz. But if you can realize this, you have to keep in mind that physically the detection threshold is still limited. You will not be able to detect objects of a certain size which falls below the detection threshold. Finally, the accessibility of an area depends very much on the takeoff and landing site. You can choose to get close enough to your site. This is a big problem, for example, here in Scandinavia in our projects, because the area is so inaccessible. We never find a place which is inside the area. So it's very important that endurance is increased to more than 30 minutes. Here you see the Fluxgate magnetometer. We use 5 of them. The total weight of all 5 magnetometers is about 3.3 kilogram, which can be easily transported by our multicopter. Of course, as you have already heard by the talk at Konyan, a Fluxgate magnetometer needs calibration. If not, the total magnetic field intensity you measure depends very much on the direction or on the orientation of the components within the Earth's magnetic field. So it needs to be calibrated. And in opposite to at Konyan, we developed airborne in-flight calibration procedure. Here you see an example of the flight pattern. It's more or less cloverleaf shaped. Usually we climb up to a height, an altitude of 50 to 100 meters above ground level to avoid interference with magnetic anomalies, if there are. And here you see the results from this cloverleaf test. In the lower panel, you see the components. Blue, red are the horizontal components, green the vertical component. If it's not calibrated, the total magnetic intensity, which is shown in the upper panel in light blue, has a variation of almost 100 nanotesla. So it's useless. You cannot detect the magnetic signature of small metal objects. But after calibration, if it's properly done, the standard deviation we have achieved is about half a nanotesla. So there is no filtering, no statistics, nothing. You see the unfiltered data, and the peak-to-peak amplitude is the residual is in the order of 1 nanotesla, and the standard deviation is half a nanotesla. So when achieving this, we choose a test site, a military test site in northern Germany, close to Hanover. It's a military training site where 53 objects of different sizes were buried, officially buried by the military. And we were asked to fly over it to test the detectability of our magnetic system. Here in the left panel, you see our multicopter while flying over this area. The size of this area is about 1 hectare, and we required 2 flights to cover this area. In the left panel, you see the flight lines, and in the right panel, you see the magnetic tracks achieved from our 5 sensors. And here we choose one flight line, where I will show the measured results in my next slide. Here in the left panel, you see the 5 tracks of the magnetic sensors and the results, the TMI for each track, because some anomalies are very, very small. I enhanced the TMI a little bit to make it clearer. And the 5 red dots show the positions of different objects, metal objects buried in the ground, known objects. Here it's shown again. The analysis revealed that from the 5 objects, we were able to detect, clearly detect 3 objects. Here, this is an unknown object, which is clearly detected, but we don't know the size of this object. This object number 52 was a 500 pound bomb buried at 2.14 meter depth. The other object number 13 was buried in the shallow ground at 10 centimeters. This is a ammunition of 3.7 a caliber of 3.7 centimeters. Number 21 wasn't detected because it's almost it was buried at almost 1 meter depth, and it's very small. It's a 3.7 centimeter caliber. Object number 29 was buried at almost 1 meter depth with a caliber of 7.5 centimeters. And the other object, 38, probably was already too far away to become detected. In this panel, you see all objects, known objects, which were buried at known depth and known object size. From this analysis, we were able to draw a clear detection threshold, which can be detected by our Pentamax system. And it clearly reveals that objects of 3.7 caliber, centimeters of caliber and bigger can be clearly detected if they are buried at depths less than 1 meter, above size of 10 centimeters. We can clearly detect it to greater depths of several meters. Okay, this is what I wanted to show you. Thank you for listening. And here you see the 4 people who contributed to this presentation. Thank you very much.
I've got a question, Johannes. This is Ed here. Johannes, now on your drone, you're within the noise, the platform noise field, is that correct? Your sensor. Well, mine isn't. So why would you do a Cloverleaf for a sensor not in the noise field?
because then it allows also to correct for the magnetic signatures created by the drone itself. If you
There
don't do
aren't
that,
any, Johannes, it's isolated from that noise. It's slung below 3.5 meters below the drone. So
no, in our case,
outside of the noise field. I understand why you would do it because you're within the noise field. If the sensor is outside of the platform noise field, you can just calibrate the sensor. I've seen you do this.
yeah.
You know, I've seen you do it. So you can do it on the ground. And I see you've said this in some of your past articles that you've calibrated sensors on the ground. So I understand why you do it. But in my case, my sensor is isolated from the drone. So I don't have to do a Cloverleaf. I can do a ground calibration, which is going to be more accurate because, you know, Magnestrode doesn't calibrate their flux gates on a moving platform in their lab, do they?
Yeah.
That doesn't make any sense, does it? It's kind of nonsense, isn't it?
No, it would be really advantageous if you can prove that your calibration done on ground also works when your system is airborne.
Yes, I can
this
do
is
that.
what I would like to see.
Gentlemen?
Yes, I can do that, Johannes. What I would suggest then is this. This is something I can do. Just do a heading check and a correction if it's necessary. You can just do a standard heading check. These have been done by commercial, you know, airborne mag contractors for decades. Also do a lag test. I understand why you do your thing, Johannes, but I think you missed the point that my sensor is isolated.
Questions?
Gentlemen,
We need to address.
Gentlemen, can we continue this during the discussion portion? We have some other questions we'd like to get to, and
Indeed.
we have a bit of a timeline.
It's all good fun. I mean, I like Johannes a lot. I like him a lot.
Ed, that I think I'll second Morgan that this is more for a topic more for our discussion phase, and please bring it back up. And this is the kind of thing we were hoping that people will get into, but there's a time and a place.
Well, I'd like to add that others would like to participate in this discussion, and they're currently not allowed to speak.
Right.
So let's continue this when they can participate.
The next presentation is by Rainier Wakterli. I hope I didn't screw up your name too badly.
No worries.
I'm an American. I just don't pronounce German names very well. Anyway, he's with a company called GeoIntrepid, and he's based in Namibia. His presentation is titled Drone-Based Airborne Magnetic Survey from a Processing Point of View. Take it away.
Can anybody hear me
Yes.
and see the screen?
Yes.
Cool. Ron invited me actually to share a couple of observations I made as an external data processor. External meaning that I'm not linked to any company, or any instrument manufacturer, or any drone contractor, or any research institution. So here there are some observations. My name is Irina Arena, working for GeoIntrepid Namibia. GeoIntrepid is the consulting arm of Intrepid Geophysics in Melbourne, and I will talk about good data, our processing toolbox, survey design, and compensation and navigation accuracy. Other than the last two talks, compensation means the removal of the platform influence and not the calibration of the instrument. So we all want to produce high quality data, but how do we define good data? So in my books, it's the consistency in itself, and the data must merge easily with neighboring surveys. Two examples: 40 by 40 kilometer 200 spaced mag line data, standard TMI product. The question here is, where is the paleo channels? And as you can see, you see nothing. But if I take the surface layer response, take its derivative, and apply and display it as a shaded image in grayscale, one can maybe see very subtle features that are a little bit duller than its surrounding. That could be interpreted as paleo channels, but paleo channels is not the point. The point here is that I brutalize the data and the data holds good data. Next example, a couple of surveys from Sweden, to also 200-meter line spacing, different line directions. One of the surveys is older than GPS, and it doesn't take much effort to actually produce a seamless image, good data. So how do we achieve the good data? While carrying our sensor on a platform that actually produces disturbing signal. So the first thing is we have to remove all non-geological information based on the principles of physics, and then please use the tried and tested tools. Airborne geophysics is around since a while. So here's a proposed workflow, or my type of workflow for 1 kilohertz mag data. We have base station, we have the drone data, and we have the magnetic data. Base station needs to be de-spiked and filtered. Drone data, position data, and the attitude angles, Euler angles have to be interpolated. Maybe you want to filter them. Mag data, first of all, you have to compensate them. We'll speak about that later. Then with the nice 1 kilohertz data, we may apply a notch filter to remove either platform noise and or cultural interference. That becomes very handy when you fly in urban areas. Then if that data is cleaned, then I low pass the data and reduce to 20 hertz, because if you fly 10 meter ground clearance or 15 meter ground clearance, you don't need to point every centimeter. And this are then merged in the combined geophysical data, and then we start with our toolbox, processing workflow. That's the standard toolbox. The compensation is colored a little bit differently because me as an external processor, I'm not involved in the compensation. So I'm starting with the flight path cleaning, and we can't talk about all of that. These 4 corrections are based on physics. Then the leveling tools, they are cosmetic, and then at the end we have gridding. You can have an entire workshop about gridding alone. There's no time, and after we have the final data, we do our secondary products, pull reductions, multi-scale etches, you have you. But the whole thing starts with the survey design, and because of the low endurance of the copter drones, I suggest a systematic approach, fly tiles and fly tiles that overlap. Each of these tiles is basically, oops, there's the mouse. Each of these tiles is basically a complete survey in itself, sufficient tile lines, everything there. And the advantage of that, if you fly tiles, is that if they're flown correctly, the data can be pre-processed automatically in the field. You fly your 3 or 4 tiles in the day, and then you plug them into the computer, and after supper, you have your QC grids. It's quite handy, but you have to adhere to sort of a systematic approach. The big problem in airborne geophysics is that all common platforms we use do emit electromagnetic radiation, be it DC, AC, they do. So we have to remove the platform influences affecting the magnetic data as good as possible, and that is what is called compensation. Each of these electromotors produce a magnetic DC mag field of several hundred nanoteslas. Luckily for us, DC shifts don't really matter. Unfortunately, the attitude of the platform with regard to the ambient magnetic field does matter. So there are 2 ways to get rid of the platform influence. The first one is mathematically remove disturbing signal based on a compensation flight or test flight or whatever you call it. Most of the stuff is based on Leliak. The other possibility is to just suspend the sensor, suspend it far enough that the platform influences are below the noise level of the sensor. One comment to that image, the extremely high accuracy squid tensor magnetometer from Anglo American was at one stage suspended by 100 meters because they had interference from the platform. But that's the thing. So compensation. Here is a little example. We don't look at the data first. That is the survey as it was flown. It's a 40-meter line spacing, 30-meter ground clearance. Unfortunately, there were on all sides of the survey area, there are obstacles. 3 of them were from the bureaucratic kind. So the turns had to be extremely narrow within the survey area. So this line here is flown from east to west. In the picture here, it shows from left to right. That's the attitude, the Euler angles of the platform, pitch, roll, and yaw. So we come out of the turn, but the platform is already facing into the line direction here shown by the yaw. There's a bit of roll involved, and then we take a little knot to pick up speed, and we proceed along the line. There's a bit of wind, presumably, and then we prepare for the next turn, and we come to a screeching halt, and we turn the shoulders, and we roll. And so that is quite a significant maneuver. And surprise, surprise, you do see it in the raw mag data. So here's our speed wobble, there's the wind noise, and here is the braking and turning maneuver. And those guys who did it actually did compensate for that. So speed wobble is gone, the turning maneuver is gone, and some of the noise here is gone. That is actually 2 thumbs up for the operators. They compensated for the platform influences. This was done on a rigidly mounted flux gate magnetometer. So here is the fourth different standard noise is a bit higher than you would expect, that you can expect from cesium vapor magnetometers. And because they did a good compensation, the data process easily. This is the first vertical derivative in the shaded version from the RTP, and maybe there are some smallish artifacts, but in general it is well compensated and good. So what I want to actually have now to compare different systems is some standardized procedure how to fly a compensation and the value band to accept it. That is commonly called in standard traditional airborne geophysics, it's called the figure of merit. Next option, suspend the sensor. This is a repeat line, 12 repeats flown in 6 blocks back and forth. Don't look at the center of the area of the line. The operator wanted to do me a favor and found some scrap metal in the field and flew over that, and tiny little navigation errors easily produce and different mag readings here. The only thing I can take from this anomaly is that there is no lag in the system. But have a look at the ends where there is geology, no cars or tractors in the field. It looks quite good. So the repeatability is quite high. If we want to quantify the repeatability, we look at the deviation from the mean. Mag IGF in my naming convention means that I did correct for the diurnal and remove the IGF field. So overall noise envelope is probably 2, 3, 4 nanotesla. There is one line that is specifically bad. That's a fat orange line, and it shows periodic wobbles almost along the entire line. The period of the wobbles is 4 seconds, which corresponds to the period of the pendulum of between 4 and 5 meter length. So if you fly 10 meters per second, you can't filter that out because that would be 40. The low pass filter 40 meters. You will reduce geology, remove geology. So the accuracy on that thing is shown as the standard deviation, which is the black of all 12 occupations, which is the black dashed line. And you know, if you eyeball the left side, 1 sigma range is about 2 to 3 nanotesla. However, I want to have more than 70% of my survey data being better than what I claim to be able to do. So we have to go for the 2 sigma range. And that would be 4 to 6 nanotesla. Now, depending on your survey objective, that may be absolutely adequate to detect your geology, whatever you want to find, but it won't find me my paleo channels. So we either have to increase the suspension distance, which could generate some problems for the drone, or we have to compensate the data. Now, compensating suspended systems is a bit more complicated than rigid systems because the entire system can move with regard to the mag field, or the position of the sensor can move with regard to the platform. So if somebody bright has a good idea, that would be great to have. Again, to compare different systems, I would like to have some guidelines and what to fly and how to do, and that I can say, okay, for this accuracy, you better fly the one system, and you may fly the other system if you only want to find some carbonyl tiles, say. Navigation accuracy. If we fly 20-meter line spacing, navigation accuracy becomes more and more important. Standard specs for line spacing is 25%, which deviation is allowed. That would be 5 meters deviation in a 20-meter space survey. Here it shows a 1 by 1 kilometer tile, 20-meter line spacing, and no, this is not a repeat tile, unfortunately. Because the blue lines show the data recorded by the Mag GPS and the red lines show the data recorded by the drone GPS. So here in the bottom, the survey base was somewhere here. At least the traverses between the two systems do agree. The tile is not that well, but if you go to the far end of the survey, then of that tile, then we have 7-8 meters discrepancy between the two data records. So definitely one is wrong. You will also, as you can see, there is sort of a systematic deviation from the bottom left to the top right. So you may be even able to process the data and maybe even result in a good grid. But if you want to merge now this tile with the next tile to the north, you're running into problems. Next, and also important, or even more important, is height keeping. Height keeping basically meaning that traverses and ties do cross at the same height, and neighboring lines are flown at a similar height, depending on the terrain. The reason for that is simple: is the fall off of the magnetic field. So the lower the ground clearance, the larger the effects of height inconsistencies. If I'm flying a regional survey above 100-meter ground clearance and I'm 10 meter, 20 meter, even 30 meters off, there's not much harm done. But the closer I come, oops, sorry. The closer I come to the area which we survey with drones, very low ground clearance, 15 meters, 20 meters, 10 meters, the more important that height keeping is, because a 5-meter height difference can easily produce magnetic misreadings of 10 to 50% of the amplitude of the local anomalies. So if you fly a 500 nanotesla anomaly and you're 5 meters out, then the mismatch can be several tens of nanotesla, which is extremely difficult to process. Example from the praxis, again, 20-meter line spacing. This is the recorded elevation, and you do see that there are height busts in, and that is the corrected but unleveled mag from that height. That thing is only all height busts, and the problem is I can't really tie line level them out because the distance of the height bust is shorter than the distance between two tie lines, which I need. The only thing I can do here is take all the stops out of micro leveling or decorrugation. I can get rid of this stripes or striations, but the data will be smooth, plus I may remove geology. So we need to go RTK, maybe even with the base station, or because RTK is for horizontal and vertical navigation, and we should develop a ground following system based on radar. The reason why I'm promoting radar is that if you fly over trees and you have a laser altimeter, you count leaves. Oh, this was my own reminder. Jan yesterday was talking about tensor mag data from drone swarms. And Jan, if you're listening, the positional accuracy is the largest obstacles to actually get mag tensor data from a drone, from a swarm of drones that are actually Laplacian. So as a conclusion, do the proper survey planning. Please use the toolbox that is available. It has been there since decades and it's working. Then yes, we do need to compensate for platform influences. Don't fool yourself. But there is no proper compensation procedure yet established. So we need to establish one and figure of merit guidelines that are suitable for copter drones. Extreme care has to be taken with the GPS and the height following system. I guess it is already in hand. A couple of groups working on that. I believe one article was in the Fast Times. And last but not least, maybe, just maybe, think about changing the platform type. This is a hybrid system. You know, the bulk of the payload is carried by the balloon, but the thing flies like an aircraft with tiny little wings and the rudder and an elevator. And in this configuration, I would believe that we can exchange the electromotors against combustion engines, which would rid us of several hundred nanoteslas of disturbing signal. Plus, it would boost our endurance to hours. The third positive of that thing is that if all the systems would fail, it floats to the ground. It doesn't crash. So there's a safety issue involved in that. And I can hear you already all crying, but what is with wind? But you don't fly a copter drone in 30 knots here either. So thank you very much. That was my part.
Thank you, Rainer. Rainer. Great talk. Are there any questions that I'm actually opening up the chat box right now to see if there's a question for you to answer?
Yep, we have received one. So bear with me. It's a little bit longer. So one issue that we found with compensation of copters is that the motors do not behave the same even when flying in the same direction. Because the motors are automatically and continually adjusting to keep the platform level. This means that in order to truly compensate for motor noise, the behavior of each motor must be recorded and time-stamped and merged with the mag data. Can you touch base on your response to this?
Yeah, we tried that. I tried that. I got data where there's motor data as well, but usually the frequency is so high. It's not a DC. They're not driven by a DC current. They're driven by high frequency current to actually ensure the ultra high response time. Those motors need to keep the copter in the air. It's mainly the DC field that is important.
Could I just make a comment? Is that okay? This is Ed here.
Sure.
Yeah, as long as it's not too long, Ed.
Oh, okay, yeah. Thanks very much, Rainer. It was a good talk, and Johannes's too. That was excellent. I mean, that system that Johannes has is fantastic. I think the thing is with that thing about copter noise. I didn't see any of my profile data. I should have shown some flight lines. That's actually another talk I have. I'm not seeing any motor noise or any kind of noise really in the flight profiles. And another thing, I think it was Walter. That's another reference in my end of my talk. He flew a GSMP 35, which is about the most sensitive and highest resolution commercial mag you can still buy, I think. I mean, I know some of the other mags, scalar mags, are catching up, the rubidiums, some of the cesium, like the MFAM and stuff, but he didn't see apparently in his paper with a super sensitive magnetometer any noise in his, and that was suspended at 3 meters. He can correct me. I think he's giving a talk during this week, but so for a slung sensor, I think as long as it's adequately distanced from your platform, and I understand the concept of the changing motor speeds, but you'd see that in the data. I'm not seeing it in the data.
You know, Ed, that's an excellent comment, and there's obviously several camps here that these kinds of topics need to be explored a little bit further in our discussion session. So I'm going to ask that we kind of put it off for now.
Okay.
And take a break. We have scheduled a 10-minute break. We were supposed to begin again at 11:40. It is now 11:35 or 36. So I'm going to suggest that we actually cut the break down to 5 minutes. Everybody go get a cup of coffee or whatever you need. And we'll be back in 5 minutes, or we'll be back at 11:40 Central Time, and we'll begin again.
All right. I know that was a really fast break, so hopefully most everyone has started to make it back. And in the favor of staying on time, we're going to jump right in. So I'd like to introduce our next speaker. That's going to be none other than Ron Bell. And he will be speaking today on lessons learned from 4 years of drone magnetometry. And his affiliation is with International Geophysical Services. And without further ado, Ron, take it away.
Thank you. Thank you, Morgan. Can you see my screen? Is it shared?
Yes.
Excellent, excellent. Hello, everyone. I'm a sort of a replacement player here, or replacement presenter. Our original presenter had a couple of weeks ago had to back out, as he put it, due to the realities of COVID-19. And I hope everything's okay with his family and his colleagues and such. He didn't elaborate any more on that. So what I did is I put together, I thought what might be a kind of a nice thing to share with you all is a little bit of my experience with using, actually starting out with the drone magnetometer, the mag arrow. Let's see if I can get this thing to move on me. So I'm going to talk a little bit about the mag arrow, and then I'm going to talk about what I started out as pre-flight concerns, that is concerns that I identified early on, and still, surprisingly, it's pretty logical to figure out what you need to do, and then you got to get your hands dirty and figure out what you learn about what you need to do. And I'm going to kind of go through, I have a test site located in Colorado. It's called the Crestone Crater. And I began in 2017 and went back in 18 and again in 19 to collect some data. And I'm going to show sort of the evolution of our process. And I'm going to show a few things of what we've been doing in terms of using the mag to locate wells or infrastructure and mapping geology. And I'm going to sort of kind of summarize what I think are the lessons we learned, the key ones, and then the issues. I'm going to talk a little bit about the issues and concerns, what we're working on right now, and then what I see as the path forward. And then I'm finally going to end up my presentation, hopefully within the period of time we have, acknowledging a few of the players that have helped me, a few of the companies that have been very instrumental. The mag arrow, this is that picture in the upper left is a prototype version that looked kind of like an arrow. In it is the physics packages, which are two CCM, optically pumped CCM magnetometers on a chip. And then there's another set of things, including a GPS for locating it and timing, the Wi-Fi system in it, and it actually had the ability to measure the roll, pitch, and yaw. Although in the early days, I did not have the ability to actually access that data. It was not output for us. But it samples at 1,000 hertz, which was well beyond my experience of, which has been with ground magnetometers primarily. And I at the time I couldn't really understand why you'd want to sample that fast or that at that rate. I have since changed my mind, and I actually think that it is, and it's almost essential to oversample. The current version, which you'll see, is that's a picture of it from a project I did last November. It doesn't have any dropouts. It has actually two sensors, but they're oriented orthogonally, and there's an algorithm that makes sure that it gives you a proper measure of the scalar magnetic field. The heading error is around 1.5 nanoteslas. The output file is binary. That was essential. The first, that was actually a very important change, because the original output files were ASCII, and they got to be very huge very quickly. And in the data file is the GPS data, the time, the lat and long, and the altitude. And then there's some other sequences in there that are common to GPS data. The IMU data, that there's an IMU in it, and we are actually measuring a direction with a compass. That we measure the roll, pitch, and yaw. That data is available, at this point in time, I've not actually utilized it, but it's available. And then the current battery configuration is about a 2.5 hour battery life. You can actually improve that. So we could fly 5-10 hours at a time and just collecting data just by changing out the batteries. Anyway, the pre-flight concerns that we had, well, how does it compare with what I was familiar with, which is the ground-based data? What drones to use? That's when you're starting out, that's really one of the big questions. Do I do a fixed wing? Do I do a helicopter? Do I do a multi-rotor? Are they electric powered? Are they gas powered? There's all those questions you go through. A lot of them have been sort of addressed, and there's been a sort of a what do you call a focus in on using certain electric drones, and now there's an improved focus on using gas electric drones. So how do you mount it? How do you suspend it? That's a big question. And then when you fly it, what altitude and what the line spacing and all of that, and how do you plan a survey and how do you process the data? Many of these topics, if you'll know, have been addressed in one way or another earlier in today's session. So I'll try not to bore you with, see if I can get this thing to actually move. There we go. So this is the very first data that I acquired with the MagArrow. And the plot to the left, on the very left side, is the ground mag survey. And the plot on the two plots on the right are the two sensors that are in the prototype version. And what you see is that the correlation between the two, the repeatability, this was done by walking the ground mag, which had a GPS in it, and then I had a gentleman follow behind me with the MagArrow holding that about hip height. So the sensor of the mag, the ground mag, was about 1 meter taller than where the sensor of the MagArrow is. So part of the explanation of the detail in the MagArrow is which you can clearly see, is due to the difference in the actual height of the sensor above the ground surface. The other explanation for the detail, I think, has to do with the sample rate. I think I was only sampling at 10 hertz on the ground mag. So then I went to start flying it, and I said, well, I got to know what my drone signature would be, and this is, I did put the ground mag that I had, and I about 1 meter away from the drone, and I just fired up the drone, and they lifted it off, and I got to measure what the magnetic field was, and that gave me a little bit more insight. And then I had them fly over where the sensor, I had the pilot fly over the sensor, and at 2 different altitudes as best as he could fly it. This is not in any way near precise. He just kind of eyeballed it. And you get to see that when we were at 2 meters, we had about a 2 nanoteslas signal from the drone. And then at 1 meter or higher, we had about a 1 meter or 1.4 nanotesla signal. That gave me a sense that I needed to actually suspend it about 3 meters below the drone. And that is an actual picture of flying down where we were using the M600 and the MagArrow prototype. And then we went out and flew our first survey, and this is our very first data set that we flew. What we learned from that is we probably flew it too high, we flew it too fast, and we had the flight line spacing too tight. And then when it turned and went back on the adjacent line, the red parts of the signal here, that's just from the motion noise of the MagArrow. It was into a pendulum, but it was the first time we'd ever flown it, so it was really I was really impressed that we got something I could work with. So the next step was to there we go. The next step was to really take it down to a site, and that happened to be in Crestone Crater. Over the course of 3 years, we flew the MagArrow, the prototype, and then we went back down last year to fly the production version. we kind of explored were short versus long flight lines, basically tiles, a lot of tiles, how we were going to put the tiles together. We played with UAV speed and altitude relative to data quality. And then we looked at elevating the pilot as a way of improving our flight operations and reducing the number of what I coined a term, I call it flight operation staging locations or fossils. So those are the places that we would actually fly from. This is the Crestone crater right here. That's a topographic feature that is theorized to be an impact crater from a meteorite. And this is our first survey where and then you can, hard to see, but I actually did a ground survey after the crew finished up collecting the mag arrow data. And I integrated, you can see there was very good correlation between the mag arrow prototype data and the ground survey. So I was on my way to feeling this is the Crestone crater. I've done a little vertical gradient on it just to show that the crater itself has a very circular and very directly attributable magnetic signature. Anyway, the next year we went down and flew a square mile, and we broke that into a whole bunch of tiles and had multiple locations. This is the flight path map from that, and that's the data from that particular survey. And then in 2019, I realized that I hadn't really done everything I had acquired down there was with the prototype. So I went back down with the production version, and I began kind of repeating some of what I had done the previous 2 years. And the first is I flew a 10-meter, the principal flight line separation here is 10 meters. And then I expanded it to do 20 meters. And then I went and we did a much bigger survey. And in order for us to actually adequately keep our attention, or the pilot to keep focused on the aircraft, which is a requirement of the FAA in the United States, I actually elevated the pilot using a boom lift. And what you're seeing on the left is the flight path map and from one fossil, from one location. He was able to actually maintain line of sight on the aircraft and the magnetometer from that one location. Basically, he had 1 mile plus flight lines. That was a huge difference from when we first started. Also, this is the data on the left, or the TMI data. I've done a little bit of processing to smooth it up and make it a little bit more cosmetically, but not a lot. I leveled it up and corrected for that diurnal. I didn't correct for any heading error. And then what's on the right is the tilt derivative. And it's a usable data set the way it is. We could actually tell some things about the geology. So the next sort of things that I've been involved with is I've been looking at how do we design surveys, what the time of acquisition will be, how do we access the survey areas, what happens if we're flying in forest covered areas, what data density and detail do I need to actually get something useful out of the data, and then look at real-time processing and visualization. Those are the types of things that we kind of addressed for the last couple of years. This is an example where I flew a mag arrow survey, located 4 wells, took us 4 hours to do it. We knew where the wells were supposed to be located. We didn't really have to vary too far away from it. I didn't have to fly a bigger area. This is a survey example from the West Texas, where we flew scanning an area, looking in an oil field, talk about noisy environment, but we were scanning it to try to see if there was an existing well in place from a legacy effort out there. And then we've flown at some mine sites, and we've flown some exploration surveys in the desert Southwest. The basic things that I think we learned is that the wind rules. The weather is really impacting how your productivity or your ability to fly, and wind is a big issue. And some of the data that you've seen people talk about really is oftentimes do with the wind. What I also concluded was that the longer the flight lines, the more preferred. That kind of also says that the longer the flight times is preferred. And then we have to adjust our UAV speed to diminish the noise. Forgive me for not putting noise there. We QA our data after each sortie. Everybody knows who's been flying drones for a while that crashes happen. But if you're prepared for dealing with it, you can be back up and flying within a short period of time. Hopefully the crashes aren't catastrophic. I'm a believer in oversampling both spatially and temporally, and it is acceptable. Often it's beneficial, and I have some examples of why it's beneficial. I'm not included in here, but I actually can see other things in the data, in the mag data that are more cultural, and that can be helpful. You can use, if you're getting into it for the first time or you're thinking about it, use a service provider rather than trying to buy everything and do it yourself. That would be my advice to anybody. And then once you've got some experience, then bring it in-house if you feel like you want to, if it makes economic sense. The things that we're actually dealing with today is maintaining a consistent altitude of the aircraft. That really leads to the use of a radar altimeter or a laser altimeter to do so. We're looking at how to deal with the heading error. It's an issue a lot of folks deal with, but we haven't dealt with it so far, and now we're looking into it. Aircraft noise is an issue. Not so much a problem, but an issue. Motion noise is the problem, or is the issue. So we're trying to deal with that. Fortunately, the mag arrow measures the roll pitch and yaw of the sensor during its flights. We want to do longer duration flights. We're improving our data processing workflow, and we're actually looking at how we can actually do beyond visual line of sight and nighttime missions. Now, the path forward for us is basically developing a protocol measuring the UAV noise signature. We're going to be using drones other than the DJI M600, ones that actually will have longer flight times. So, but we have upgraded our, and when we use those, we need to know what the noise signature is. So we've developed a protocol. I'm actually going to publish that probably in the next month or two. Then the M600, we've upgraded it with the radar altimeter from SPH Engineering, and included, we're currently testing the UGS terrain following process software. We recognize that RTK is essential, particularly for very tight surveys. We're actually fabricating a rigidized suspension system so we can reduce some of the motion noise. Eventually, we'll be looking at a fixed wing UAV installation of the MFAM sensors. We're improving our motion noise corrections. We're enhancing our data flow and all that other stuff. I wanted to make sure that that these folks were acknowledged. I don't often say it to them as much as I should. They've been very helpful, particularly Geometrics and Sequent, and actually helping over the last 3 years kind of either develop tech or work with them to develop tech that, particularly processing tech, to actually improve the data quality. Skyscopes and Juniper Unmanned were our service providers that own the Magnetometer, and I've been working with them. And Collier Geophysics is actually a geophysical consulting firm that has flown a number of Magnetometer surveys. I've been fortunate that I've actually had a chance to work with them on that. Anyway, I'm ready for questions if there are any. Thank you.
Ron. So we have a couple questions, but you used up all your time.
No, I tend to do that. I drone on. I will answer them online, or I will put them on the put them into the discussion area.
Thank you very much. All right. So our next presenter is going to be Juan Ortega. Sorry, mispronounced the end. And he's going to be sharing a talk with us about an unmanned aerial vehicle magnetic survey to locate plumbed and abandoned O&G wells prior to construction of an industrial facility in Southeast Texas. and he is affiliated with Drone Geophysics. So Juan, if you're ready, you can go ahead and share your screen.
Right. Well, thank you, guys. Yeah, like Morgan said, my name is Juan Ortega. I'm part of the Drone Geophysics group, and today's talk will be on a case history of a project that we did down in Texas. I want to thank Ron Bell for helping us execute this project, and our client, Brad Cross. I just briefly want to mention some of the talking points that we'll be going over. These are some of the ones that I'm going to focus more, and I just want you guys to take away some of these major points here.
Juan, I'm sorry. Your mic, I think, keeps hitting your shirt collar, and it's crackling.
How about there? Better?
It's
No?
still crackling.
Give me 1 second. 1 second here. Let's see if I can.
Sounds like your mic is rubbing against your clothing.
Yeah, let me see here if I can. I'm trying to, okay, here it is. Let's see. You guys hear me there better?
Yes. Mm-hmm.
Okay, I changed the mic, so this should work much better. So yeah, these are some of the projects that we've worked with, some of the different sectors, as well as the different clients that we've worked with to execute oil and gas finding oil and gas legacy wells, as well as for other type of sectors in the geosciences. These are some of the benefits of UAV surveys. I'm sure everybody has mentioned a lot of them. These are from my experience, some that I can take away from, especially in this project. Of course, accessing difficult sites, lower operation costs compared to a helicopter survey, and immediate generation of magnetic map, and safety of field staff, of course, a priority, as well as multiple data types and faster acquiring of data compared to a ground mag. I want to quickly jump into this ones. Again, these are some of the limitations and restrictions that I've come to knowledge on my experience. A lot of them, weathered, vertical structures, short duration of flights, some restrictions, visual line of the site. We can only operate during daytimes, and one operator per one UAV, of course, as the other ones. I thought this slide was really important. This one here really talks about the actually response of wells, vertical and horizontal structures on ferrous materials. We can see this was a ground-based magnetometer survey that was completed back then in the 80s, locating an oil and gas legacy well, doing a ground-based magnetometer. We can see that a big takeaway from this one is that we can actually find abandoned wells by using magnetometry. Now jumping to the project that we completed, the project overview was here to assist WSP in investigating a 247-acre lot to determine the precise location of a few abandoned oil and gas wells, as well as to scan some of the some of the pipelines and other buried materials, if any were left behind. What was the problem? So for this project, the client had performed. The client had performed a ground mag survey on this site prior for us coming in and executing the drone survey, but he had no luck in locating the well. Again, this location had a very thick vegetation. that was one of the problems. A second problem, being located on a down in the Gulf, it was a lot of the site had marshy and wet areas that diminished the execution of actually doing it by a ground-based magnetometry survey. The client had collected the data, the legacy well data from the Railroad Commission, which is a Texas public database domain that anyone can come in and look and access to see if there are any wells within the area of your interest. But again, databases like this one, especially when locating legacy wells, some of them are pretty historic wells that were not either one, logged at one time, or two, were poorly logged. So might be off a few or even 100 feet off. The gear that we use for our survey, of course, we use the M600 Pro, a Mag Aero for the magnetometer, as well as the for the base station, a Geometrics A58. Here, just briefly mention the UAV flight specs that we use for the survey. Again, considering the type of size, like Ron mentioned before in his presentation, depending upon the size of the actual location of the property, how big the size is, that's how we came up with the how many flights we needed to do, and where do we need to station the pilot for him to have a good visual of the drone and not lose the sight of the drone itself. We collected data, 23 miles of line magnetic data at a speed of 11 miles per hour. Here in the field quality control, myself and the drone pilots made sure that we were actually collecting the data where the drone was going where it needed to go. So we did on the 8 flights that we did, every time the flight would come down, I would download the data and start QA/QCing to make sure that we were actually hitting the spot on the flight specifics that we needed to complete. Of course, we also started grading the files to start actually contouring the magnetic data to start looking and seeing if we were able to hit the actual well at the location where the client said it would be. This data processing flow slide just mentions what we usually do. Again, a lot of these ones here are for post-processing. We would jump into the, we would go, once we get back from the site, I was able to start processing with the help of Ron and my other colleagues. We started looking into the data and actually continuing the flow of this processing until we finished to the executables. Here we can see the actual executables once we completed the surveys and we processed all the data. We did saw that the well was off from what the database had that the client provided us. Of course, the client, per the client in his survey that he did before, he did excavated quite a bit before we came in, and he dig and he did the ground survey and he couldn't find it. So of course we were able to locate it, and it was actually 227 feet off from the database that they had. So the well was off by 227 feet. In here, this is a really interesting processing algorithm developed by Ron Bell that really brings the anomalous, in this case, the wells and the metallic pipeline that we can see here, which really brings it up into a level that it kind of windows the other data, but it really brings the data that we're looking for, which are all the metallic and ferrous debris that are in that particular site. Again, this picture is really of interest. The client, after we delivered the executables, he gave us the picture of the actual finding the well after they had spent a few times doing the ground survey before. As for summary, we were able to collect data over 247 acres. We were able to identify the presence of the well within hours of the acquisition. And we were actually able also to give an approximate depth of the identified for the client, for him to excavate to find the top of the well. A pipeline was also identified within the same data set collected, which was great for them. And as conclusion, a UAV drone magnetometer surveys are an efficient and cost-effective way, I believe, to identify abandoned wells and pipelines. And within that, I want to thank you guys.
All right, thank you, Juan.
Yes, well done. I currently don't have any questions for you, but people might be sitting and thinking about that a little bit. So, so the first one that came in asks how long it takes to process 247 acres.
I believe that data, it took us around, well, it took us about a week, I want to say, to fully get the full spectrum of the executables for us to deliver. But again, the initial processing, you can start to see, we were able to start to see the interest, which in this case were the wells and the pipelines. But by the end of the week, we were able to actually send everything to the client and for him to do the excavations. Thank you.
The next question is, can you determine if a well is inclined?
That's a good question. I haven't been exposed to that. I do want to say that being the well being oriented vertical, it gives a big anomaly, positive anomaly, monopole that actually you can actually tell where the well is. If a structure it's oriented horizontally like a pipeline, you can see that it will start to give you a dipolar anomaly. So you'll be able to see the positive and the negative coming in. Now, as an incline, I want to say you would be able to see the dipolar anomaly, because you can have the well oriented. Yeah, and it will give you both anomalies readings.
Wonderful, thank you. The next question we have is, what did you use to program the flight path, DJI software, or something in-house?
No, for this project, I believe we used Litchi. I believe we used Litchi. Yeah, we use Litchi, yes.
Thank you. There's a question, how did you identify the pipeline again? Is it located at the very boundary of the survey area?
Yeah, I can quickly show you guys. I probably went a little bit faster, but when we got to the side, it's right here. When we got to the side, we were able to see that something was different. The area was mowed, and you can see that something was there. And then with the data set, it actually kicked in pretty good, pretty impressive for us to see it, even that it was located right upon the boundary of our survey limits.
Wonderful. Well, that's all the questions for the moment. Please keep an eye on the chat in case any additional questions come up. And if not, we can go ahead and introduce our final speaker for the day. So Jose Ortega is our final, Jose Arce is our final speaker of the day. He's going to talk about UAV magnetics at the Tambo South Project in Peru, challenges, results, and safety. And he is with Arceus Geophysicos. So Jose, are you ready?
Yes, absolutely.
Wonderful. My apologies about mixing up last names. I got lost in my program for a second.
no problem. So, can you see my screen now?
Yes, we can.
Okay, very good.
So,
Excellent.
whenever you're ready.
Okay, I'm going to talk about the Tambo South project. This is a project where we conducted some very interesting experimentation and comparisons with a regular HeliMag survey. This is an extension of some information that was presented originally with Vale people and Thelma Isengard, Carlos Cifuentes from Vale, and myself in Chile. And then there's additional information in here. This was a case where we were able to see the advantages and disadvantages between a regular HeliMag survey and a UAV survey. So here we go. So magnetic surveys have been used for decades in mining exploration. And large areas have been covered with airborne magnetometer surveys, what normally small areas with ground surveys. The problem is that there's a gap in the survey area, you know, that is between maybe, it is relative, of course, 500 and 1500 line kilometers, where it's too small to bring in a helicopter or a fixed wing, and it's too large to do a ground survey unless you do with multiple magnetometers, which can be done, of course, you know. So over the last years, multiple UAV capabilities have been developed for geophysical applications, you know, and we're seeing a lot of them here, and trying to target also in these particular mid-size type objectives. The UAVs provide a semi-automatic platform with faster coverage than ground survey, and there's certainly advantages and disadvantages to its use. One of the advantages are definitely lower logistic costs and mobilization costs. And also they require less maintenance and personnel than a conventional fixed wing or helicopter survey. These costs that you see here on the chart, per line kilometer, clearly indicates that for a small survey of under 1,000 meters, 1,000 line kilometers, a HeliMag survey will always be the better choice, you know. And but when you reach 1,000 line kilometers, you already are coming close to the cost of a UAV mag and ground mag, you know. So it needs to be evaluated which is more convenient. These costs here are obtained from an average cost that is used in Chile, and so this is just a reference, but it shows that the larger survey size, the more convenient to do HeliMag is, you know. So now the Tambo South project is located 1,100 kilometers southeast of Lima and 10 kilometers northwest of the city of Moquegua. So our base station was located in Moquegua, and we traveled through the Pan American Highway daily. The problem was that it was a long drive. You know, it's only 10 kilometers in straight line, but it was about an hour to 2 hours daily driving because of the distance and the crossroad we need to do. The geology of Tambo South can be seen here. Is basically the upper Moquegua formation of tertiary age, and this is mostly clay and interbedded sandstone formations. So pretty flat, geologically speaking, as you can see. There's a lot of cover here. So the equipment we use here was a BFD systems, a heavy-duty drone with 8 motors and 4 22,000 amps per hour batteries, with a maximum payload of 17 kilograms and an autonomy that ranged from 15 to 45 minutes, depending on weather. In this particular case, as you see on the photograph, the area, yes, was flat, but it wasn't that flat. There were a lot of creeks, very sharp creeks that you cannot see actually from this photograph, but it wasn't as difficult as many of the areas we cover. The use of a very powerful drone was necessary and you know, definitely was an advantage due to the strong wind we had here. The sensor we used was a GEM Airbird, a potassium vapor sensor system with a laser altimeter, GPS, IMU to measure pitch, rho, and yaw, very high sensitivity of 0.0002 nanoteslas per hertz, and a heading error that was quite small of 0.05 nanoteslas. We used a measurement frequency of 20 hertz. The base station was a GEM proton precision magnetometer with 1 Hz frequency in measurements. To better understand noise and properly separate signal from noise, accurate measurement of pitch, roll, and yaw is very important. The airbird system does provide this information within a bird, so it's a full bird and only weighs 3.8 kilograms. But definitely having a bird as such is also problematic when you have wind conditions. So to do proper tests, these are 3 tests we did at 3 various elevations. The first test was done at sea level in Lima with the airbird sensor. You can see it hanging there from the BFD drone. Then we did a test in San Mateo, also in the state of Lima, not the city of Lima anymore, at 2,500 meters elevation. And then finally in Ticlio, at 5,100 meters elevation. As you can see in the photographs, the Ticlio and San Mateo photographs, we didn't do this test with an airbird, but we used a dummy, just to be sure we were being safe. This is the first times we were flying at that high height, and we wanted to make sure everything worked perfectly. So we created a dummy, exact dimensions as the airbird, exact balance weight as the airbird, and that's what we used for testing. So once we were able to get proper navigational and computational parameters with a manufacturer for the drone, to make it more stable, and we had different propellers made for high altitude, we had to get different operating parameters for the drone. So these tests were very important to do prior to any kind of survey. The next test we did is a sensor interference test by elevation. So basically on the x-axis here, you can see on the marks of meters above the sensor height. So we set our airbird in the ground, and we had the drone fly in multiple times, northwest, east, north, south, east, west, over it, at various elevations. And we could see that most of the noise effect caused by the drone were 3 meters above the sensor and below. The noise then started decreasing, certainly, and here we're going to about half a nanotesla error range. And then finally at above 8 meters separation, we got a much smaller noise, So this is basically the reason why we use 10 meters, particularly with this drone. It's a very heavyweight drone, but it produces also more noise. So it's critical to keep it at a separate distance for clean signal. So the survey was small. It consisted of 181 line kilometers, which were completed over 7 days. They were short working days because of the strong wind. The drone handled really well in the strong wind, but definitely battery life decreases a lot. We only had about 3 to 4 hours of good flying time, considering that you need to change batteries and do a constant takeoffs, several takeoffs a day. So it's not a very long working day, and we had to repeat here 17 kilometers due to the noise and stability caused by the wind. So we used overlaps of 250 meters within lines, and the ground clearance varied between 35 and 50 meters. The design was done during the course of the survey. We used a total of 3 base stations due to accessibility issues and complex topography. It's not very easy to access this with all these very steep, small, but very steep creeks all over the place. So bases were located in areas where we could maintain as best as possible line of sight with a drone, which is a legal requirement in Peru. Blocks had an approximate north-south length of 2 kilometers based on the short battery life we had due to the winds. Base location and daily flight programming are fundamental for production, as all of you know, and flatline programming was done with UGCS. The BFD systems drone allowed us to have 25 minutes of flight in these complicated wind conditions, which was very good. In the survey design, ferry time needs to be considered between bases and lines for safety operation. And this is something I will discuss further on. This graph shows just an image of design and of the lines done by UGCS and how ground clearance is planned along the lines, you know, to be kept at least 50 meters. Definitely when the drone is climbing the upper part of the creek, it will come closer to the ground, you know, and this is where other factors need to be considered. Waypoints and line design are very critical, you know, and do blocks depending on the battery life and on the local conditions. So to do a proper line design, we opted for two options. The first option, we purchased a DTM from Intermap with a 10-meter cell size, which is the one that you see on the left, and it actually looks pretty good, you know, but the DTM that we reconstructed using the laser altimeter from the Airbird gave us the image on the right. You know, they seem pretty close, but the reality is different, you know. So when we do a comparison, this is just a random line I picked. You know, we have the laser altimeter graph for the line 14,300 on the top. And then you can see here the creeks, you know, right away. And then the DTM from Intermap shows the red line, which is actually a very smooth line. But the DTM calculated with the Airbird is a very different DTM. You see the areas where you have creeks, the Intermap image is very, very smooth, and you can reach a problem with safety here. The DTM difference between the Intermap and the Bird DTMs can be seen on the bottom image. And there's some errors in this line that there's up to 22 meters difference, you know, and this is not an extremely abrupt area. There's these small creeks there. If there's larger creeks, this can be done. This can be even more critical for safety. This was a fairly easy area to fly. So we had an accident that occurred in another project, and this is from a document we published, a paper we published, in which the problem was actually trusting what the software was doing. We programmed 50 meters above ground using the laser altimeter, and the problem is that the laser altimeter information was not being considered in that case by UGCS between the base and the line area. So it just lifted from the base 50 meters, and then it flew on a straight path to the line, to the area where the lines were located, and then it was going to do proper line following at 50 meters. But the software did not consider keeping the altitude exactly at 50 meters in the ferry distance, in the ferry area. So we had a crash, you know, and this is something we were not expecting. And then when we checked, definitely the drone just flew on a straight line and got the 50 meters from the base and flew on a straight line, and there was a small hill and it went right to it. So we lost a drone this way. We definitely talked to the UGCS people, and they did an upgrade on the software. And this is not the only software that may have this problem. So you need to be careful with the programming, you know, and but like Ron says, we all have had some crashes. So the survey was monitored in real time with the information the Airbird was sending by radio to our base station. So we could see the pitch, row, and yaw constantly, and we could get readings. Actually, when the accident happened, the Airbird kept transmitting. So we never lost communication with it. We lost communications with a drone, but not with the Airbird. So we were able to find it quite quickly this way, you know, using the coordinates there. And, you know, it was still transmitting data. So anyway, some of the problems we all encounter are dead zones in depending on the type of sensor. Potassium vapor does have dead zones, and you need to be very careful with that. And data jumps in overlaps. This was very standard issues. Some areas we had too many sensor dead zones, we had to repeat lines. This was mostly due to wind. You know, the vapor, potassium vapor sensor has a fairly small lock window. So you have to repeat some areas if there's problems with wind. We're working with some improvements on the Airbird structure itself to make it more stable right now. So basically, these are some of the results we obtained. These are the RTP. LL is a reduction to the pole for low latitudes obtained with the Amira routines. And then the ASVI. Clearly, you see some very detailed information out of the drone survey. If we do a incorrectly named tilt derivative, it's actually the inclination of the derivative, but it's now known as TDR. So we tend to accept this name. or the horizontal derivative of the DDR, you obtain these very detailed images with structure coming also from depth, you know, so it's very interesting. Now, let's compare this with the HeliMag info. Okay, so you have the two areas here, you know, the UAV TMI and the HeliMag TMI. The UAV TMI was done with flight line spacings of 125 meters, and the HeliMag was done with 250 meters. So to make them comparable, we eliminated for this purpose every two line on the HeliMag, on the UAV mag survey, so they can be compared. And here you have that result, you know, so you can easily see that there's some more detail. All of the main features are there in both maps, you know, but there's definitely more detail on the UAV survey on the HeliMag, which should be expected, you know, so no surprise here. The ground clearance for HeliMag was 100 meters, and the ground clearance for UAV was 35 to 50 meters. So comparing one of the lines here, we did, the TMI HeliMag line was the red line that you see here, and the drone line was the green line you see here. So doing an upward continuation of 50 meters to the drone mag, you obtain the magenta line here, so which is very similar to the HeliMag. Makes sense. We're flying at 50 meters, the UAV, and the helicopter was at 100 meters. So they should be very similar, mathematically speaking. So, but the problem, what we want to show here is actually the loss of information that you get in detail, you know, when you fly a HeliMag survey compared to a drone survey. You know, so a lot of the structure and detail is lost. Well, the modeling, when you first do an MVI modeling of both projects, you know, and you look at them, they tend to seem very different, you know, but the general modeling results are the same, you know, and you can see it from the areas that have higher amplitude of magnetization, that they coincide. In the case of UAV, there's a lot more detail within those areas. But these main features, you know, are the same. You know, the only area where I found a difference was this point in the UAV mag that had much better definition than on the HeliMag. So they are used for two different approaches, you know, so it's important to try to understand which is more convenient. So if we overlap now both surveys, you see that most features are contained within both surveys, the UAV and the HeliMag. But definitely we get more detail in the HeliMag, which is what we were expecting to find. So that would be the end of the presentation. If you have any questions.
Great, thank you, Jose. Excellent presentation.
Thank you, Lori.
Wonderful. Well, we have one question. What is your wind limit for operations?
I think we don't have a number for that. We use, I don't know how you call them in English. You know, these flags that you use in airports, you know, orange flags that are tubular in shape to see the wind direction and strength. And we use some wind meters, you know, when we find it is very strong. The limitation here is more of a speed limitation more than a wind. I've flown this drone in very, very strong wind and it has no problems. You know, it's really, really powerful, but it's a cargo drone, basically. You know, it lifts 17 kilograms and we're only using 3.8 kilograms from that payload. The problem here is not that, is that in order to have a stable sensor, you need to keep a fairly high speed. In the case of the Airbird, you need to go to at least 13 to 15 meters per second, which is very fast. You know, with this drone, we can go 20 meters per second, no problem, but wind will be a problem then. When you're going uphill in creeks, certainly the drone loses speed because the power is more focused in lift. And in that case, we may have noise problems. So ideally, we try to maintain 13 meters per second speed, and definitely we have to be super careful with battery lifetime.
Wonderful, thank you.
I actually, to add something to that, I tested the drone in the factory in the US in a day that was so windy. This is in Pennsylvania, that the trees were moving all over the place, and the drone was super stable. We could get it to fly and do everything. Battery didn't last much though, but it worked.
All right. Well, we have a couple more questions.
Yes.
The next one is, did the 10-meter separation from the drone affect the positioning of the sensor, especially at faster speeds and higher winds? Does the airbird also have a GPS to see what the line path was?
The answer is yes. We did a lag correction. We have a GPS in the airbird. We have the radio communications. Everything in the airbird is just like a HeliMag system. You know, it contains everything in it. So you have communication with a drone separate from the airbird. But the answer is yes. We did a lag correction.
Thank you. The next question is, in mountainous areas, how could you replace the drone batteries if you need to measure some long measurements in inaccessible areas?
Well, you have to bring it back. There's always going to be areas that are not accessible. You need to do more bases close. You need to do intermediate camp locations. It's more difficult, but it can be done. So it's more planning, of course, you know, that's where I go, but it's not impossible. Definitely, to me, it's very critical to keep line of sight, either eye line of sight, you know, or binocular line of sight, or communications line of sight, you know, and I think that's very critical with what happened in the accident we had. You know, if we would not have had communications between the airbird and our airbird base, it would have taken us a long time to find it, you know, so it's important to be communicated with the system.
Awesome. All right, our next question is, was the flight set to maintain height above launch, or was it terrain following, height above the ground? I ask because a lot of folks new to flight design assume it's all terrain following when many flights are relative to launch location.
No, it's terrain following. Definitely, it's important to do terrain following, particularly if your topography is not flat. If it's flat, you can go on a fairly stable elevation above ground. But the problem, like I said, with the program was when we set 50 meters above ground to do terrain following, and the drone lifted from base 50 meters above, it did not consider the terrain following in the ferry area, you know, and that's programming. That's programming by the software that does the programming. It's very easy to solve. You know, you just add more waypoints, you know, to the flight program. But we didn't know. We were expecting this to do this in the entire, from the moment the drone lifted to the moment it returned, it did terrain following, but it wasn't doing that. So it's a minor glitch, you know, but all these techs are being improved, so it will take time.
All right. The next question, and then I think this is going to be our last question before we transition. How do the volumetrics compare in the modeling of the UAV versus HeliMag on the last slide? Could the higher resolution UAV lead to different interpretations of, say, mineral deposits?
Well, mineral deposits, unless you are targeting vein systems or VMS systems, you want to target small objectives. You know, in this particular case, no, it was a copper porphyry regional campaign, and actually the HeliMag survey was much larger than the UAV test we did. You know, so the detail is always good. As a geophysicist, I like detail. I think we all do. You know, it's good to see structure. It's good to use more information to do better interpretations, for sure. But you work with what you have, you know. So in this particular case, the detail was actually very nice, you know, to have, you know, to do much better structural interpretation, especially. But it didn't change it for the company, because it was a test in many ways, you know, to compare with an airborne survey, heliborne survey, and to do a bunch of other testing we did, you know, and corrections with them.
All right. Well, I think we have one question left, so I'm just going to go ahead and pose it to you.
Sure.
Would you find it more effective to purchase a DEM or create your own with photogrammetry when using the UCGS software?
I would find it always better to either you collect your DEM with a photogrammetry system or have a company do it for you. I am not doing these flights after that accident without having a proper DEM before. And in our country, you know, even in that area that you saw very flat in that photograph, it's not flat, you know, so danger of crashing is very high, you know, so no, I will not do any more flights if they are not done properly by photogrammetry before.
Wonderful. Well, thank you very much for your presentation.
Thank you, Morgan.
On that note, we are going to transition over to our discussion portion. All right, we have our first panelist question. What is the ballpark range of entry-level hardware and software costs for a drone magnetometer system, including base station magnetometer, minimum GPS system? Would anyone like to address that?
I can. For a cost-effective one, which is, you know, if you're a small contractor and consultant like myself, you can get the whole system. You can pick up you know, like a used scalar base station, you know, for $2,000-3,000, a good one. And the drone, if you're just going with standard GNSS, you know, which does have some issues as far as positioning offsets compared to, say, an RTK, or what was seen yesterday with the RTK and the active terrain drive. If you just go for a standard GNSS, like an M200, you're looking at about, this is in the US now, you're looking at about maybe for a new one, about $6,000, somewhere there. And Fluxgate vector magnetometers, high quality ones, the prices vary quite a bit. You can look at several manufacturers. I'm not going to pick any one. I've used the Census and I found that quite effective at mapping. You can contact them. I'm not sure what their latest price would be, but the range, what I've seen for a good Fluxgate, just a single sensor, you're looking between 3,000 to let's say 13, somewhere in that ballpark. The highest end about 13, 14, single sensor. Manufacturers are in USA, the UK, Germany. So those are the ballparks I've seen.
Would anyone else like to add to that? All right, I'll take that as a resounding no.
I'll make a comment. The Mag Arrow is a $40,000 magnetometer, somewhat out of the price range of many, but not out of the price range of all. The DJI Matrice 600 all in, probably around 15K. When you figure that you need spare batteries, a generator, all that stuff so for something on the order of 65 or 55, you got to add in a base station magnetometer, and that's probably another $7,000 or $8,000. So something on the order of $60,000, you can outfit a pretty decent system. I don't know what the GEM systems magnetometers cost, but I suspect they're probably a little bit less as costly than the Mag Arrow. But that $60,000 is not a bad price if you've got the work for it. It's something that a lot of companies would seriously consider. The issues, though, that we are dealing with, and I think we're somewhat represented in fact, well represented in many of the talks, are the navigation issues, what impact that has on the data, the sensor altitude above the ground surface, how to maintain that. One question that has not, I have not heard many people talk about, but we tend to consider that we're going to be collecting our data as a drape survey. And I'm of the mindset that maybe we ought to rethink that a little bit and just consider collecting the data as a constant altitude survey, or constant on a plane above whatever our target is. Obviously that as we move forward, I think it'll become one of the issues, one of the operating issues that we'll be dealing with. The heading error can be an issue. The noise and the data that comes from line-to-line leveling, as Rainer pointed out, is kind of a cosmetic thing, but it really isn't. It really is a part of the process of dealing with do we have a data set that we can adequately model? I believe that knowing where that sensor altitude is above the ground surface and having a decent DEM, whether you collect it yourself or you buy it or whatever, that helps with the modeling effort, and hopefully with the precision of the modeling. But at the end of the day, one of the things that we really need to look at is the applicability of the data, even if it's noisy data, to the problem that we're trying to address. And sometimes we get so sort of wrapped up in specifications of instrumentation and noise levels and stuff that we're not really, we kind of lose sight of the fact that the data is still very usable, even if it is noisy. Working on the problem of improving and reducing the noise and identifying the noise and is definitely, we're in the process of doing that. That's actually what I heard, or what I got out of all of the presentations today, was that, yeah, these are things that are recognizable, but they're also things that we can actually come up with solutions for. And in a way, that's actually good. I'm glad we have this workshop more than in a way. It is very good that we have. Hopefully, folks will reach out and start working with each other, and we'll start coming up with solutions to some of these, what we've identified as some of these issues with doing drone mag surveys.
Hey, Andrea, I just sent invitations to you and Mike Hobbs for WebEx meeting. Hello.
Hello.
Thanks, Ron. I think Alan, okay, there we go.
Yes, I got him. Jeff has a question. So Jeff, if you'd like to unmute yourself, please ask.
Okay. Anybody hear me there? I've got it. Oh, yes. Yeah, it looks like it's coming in. Okay, good. I just wanted to ask if anybody was using any sort of active collision avoidance systems on their drones. I'm particularly interested in lower altitude surveys, like the UXO one, and flying at meter or even sub-meter altitudes. What sort of collision avoidance techniques are currently in the works?
Well, I can address that. Yeah, I've tested that unintentionally. The Matrice drone that was used for the landfill, well, as the GNS wanders during flight, sometimes the altitude of the sensor and the drone got pretty close to the ground surface, and when that is set on active inside the DJI Matrice, that sonar and light-based system does actually sense bushes and the ground, and will sort of do this without crashing into the ground. But that was early days when I was just starting to test the thing out. So it does work. but it's not to be relied upon to avoid a collision with the ground.
I'd like to sort of address that problem as well. Most of the DJI drones have some sort of collision avoidance technology on, at least the higher end ones do. And not all, but a lot of them do. And they're actually, they're somewhat inspirational, because, to me at least, because that means that to add collision avoidance to our sensor or to our payloads, which are, at least in my case, are they're hung below 2 to 3 to 5 meters below the aircraft, is a doable thing. The technology's there. The technology that is being put into automobiles currently can be applied. I don't know of anybody that's actually doing it as yet, or at least talking about doing it or have done it. But it is doable. I mean, it's we could see I could see it coming. It's just a matter of most of us are dealing with the noise issues rather than worrying about avoiding stuff. The pilot's job is to make sure that the aircraft avoids stuff, avoids hitting stuff. So that's our first line of defense right now. So.
And you have to be a little bit careful with where to place that sensor, because if you have a drag drone, drag bird, and we had that, I had it once that the laser altimeter actually suddenly caught sight of the bird, and it produced a whooping close to 6G maneuver by the drone, and it didn't survive it.
It also looks like Kian, one of our speakers from yesterday, had a comment about this as well. Kian, unless you would like to unmute yourself and make the comment, I can read it. Also, if you would like to speak, it's easier for us to see if you turn your camera on as well. So Callum, I see your hand is up. I just wanted to share Kian's feedback before we switched subjects. So Kian said the DJI M600 Pro that most folks have talked about using does not have a 360-degree obstacle avoidance, and it will fly directly into obstacles. So that was his feedback on the subject. Callum, I will turn it over to you.
So my experience with avoidance systems, and one of the things that's, I think, a misconception with this is that most of the early UAVs looked at their elevation based off pressure changes. So I was flying back in like 2017, 2018, some low surveys, like 10 meters off the ground. When we set our home point, it sets the pressure based off that, flies up to 10 meters based off the pressure change, and then does the survey based off this. So throughout the day, if you have a pressure system move through, you can basically watch the drone go down closer to the ground throughout the survey. I'm not sure if this is still the same systems that are used on some of the more advanced drones that are out now, but this is maybe something that people should keep in mind if they're looking at these systems, especially with near surface flights.
Yeah. I think the M200 has active sonar and optical sensors for avoidance. They do work. There were some bushes at the end of the landfill which were quite high near the fence, and I did fly into those without crashing the drone. It was interesting how it worked. It would fly up to the bush or tree and sort of like not know what to do. It would kind of slowly then sort of get its way through it, go to the next line and come back. So it's, you know, that wasn't intentional. It's just how the early flight line programming, not getting it perfect. But yeah, it actually did work a bit.
Wonderful. Well, unless there's any more comments that would like to be made, we've got a couple more questions that have come in.
Colum, did he answer his question? He still had his hand up. And then I put it down. And so after Column, then we can go to Adam.
So I think we still have Kian's question. I don't know if people are having difficulties putting questions in the Q&A, but it's easier for me to make sure that I see them all if you put them in the Q&A rather than in the chat. Adam, if you want to go ahead and ask your question, I can read these after.
Yeah, thanks, Morgan. Just a little feedback on the Q&A. I have the question and answer window open, and I don't see any way to enter a new question. But regardless, so I hear this DJI brand being used a lot for all these different drone applications between yesterday and today. I know there are concerns about using the DJI products for national security applications. A lot of the stuff that we've seen throughout this workshop has been environmental in some way for sensing the subsurface using drones. Are there any other drone companies out there that are building something similar to these DJI products that are maybe American made or some other country that's not maybe high on the list for national security?
I'll take that first, I guess. I'm not sure. I think with DJI, because there's so many system developer kit third-party softwares out there for flight control, and the convenience of being able to pull in a LiDAR, like a 1 meter resolution surface to control your flight, even if you're using a standard GNSS. It's because of that. It's availability. They're sold here in the United States. There's a big DJI stored right down in the southern part of the town here. So I don't know. I'm not really up to date on the national security thing for just consumer off-the-shelf drones like that. I guess DJI it's popular because it's quite a good product, and that's my experience with it.
Yeah,
I can't make that case.
There are some American-made drones that have received approval from the, I suppose it's the Department of Defense or the Interior, one of the government agencies for use on government projects. One of them, I believe, is the drone that Jose was flying, the BFD. That's an American-made drone. Go ahead, Cian.
Thanks, Ron.
Yeah, I just wanted to comment on that quickly. So Ron, there's the DoD, the Department of Defense approval is there's a new program out through what they call the Blue Skies, and so they've sort of approved for DoD use a series of, and they're all small, equivalent to like a DJI Mavic. So they're flying cameras basically. DOI has a separate approval process, and so I just want to clarify that the criteria that the two agencies use are different, but DOI has approved for purchase for DOI some of the Blue Skies programs, but they're totally separate. But along those lines, so there are other companies out there that are developing US built systems. They're just, the question is part of sometimes the scale that you're looking for. So for example, in our agency, we have 500 to 800 drones. So when we're looking for a company that has long-term scalability and support, that is an issue versus somebody who has more flexibility in terms of looking for a drone that might work for, a few flights or a year or two survey for one individual. But there aren't that many out there in terms of heavy lift payloads along the lines of what we've been talking about.
Yeah, I think you bring up an interesting point, is that generally with geophysical systems, we're looking for a heavy lift drone, and there aren't that many options available. Johannes, I'll let you speak.
Yeah, I want to make a comment on this. We are building our own drones all scales from a few kilograms up to 25 kilograms, which is currently the limit, not to go beyond restrictions for heavy lift drones. But multicopters are scalable. If you need to have a heavy lift drone, for example, to lift, if you want 20 kilogram, this is also feasible because multicopters are scalable. And if we can build this. This is we have two aircraft engineers in MGT who are able to to build this. Yeah, currently we have a 25 kilogram drone. 25 kilogram means the maximum takeoff weight. So and all our drones we have built within the last 4 years are optimized for long endurance. So long endurance is always a question of a few parameters: the battery, the power consumption, also the propellers. Yeah. So this can be estimated using a synthetic model of a multicopter. And if you like, we can design for almost any purpose. We can design a multicopter for your special tasks.
Yeah, I think Johannes makes a really good point, is that the multicopters are the components are you can acquire, and you can build the drone for your purpose. It's probably much more expensive than a DJI drone because you really aren't taking advantage of the big market that they've created. One of the reasons the M600 is actually so popular is because it is a very affordable drone for most folks, and it's a very reliable drone. But that doesn't mean it's the best. It just means that it's workable. What I see is that as we move forward over the next course of the next several years, some folks will start building drones that are integrated, that have sensors that are integrated with it, that are for a specific purpose, and they'll probably be using rather than let me start by saying that in the airborne geophysics community, you tended to use an aircraft that was built for a different purpose than geoscientific data acquisition. In the drone community, there's really nothing stopping us for actually building drones that are designed for the specific purpose of, let's say, magnetometry, where we're basically building everything into the drone, including the compensation, including the ability to fly it know where that drone and that sensor is in the 3D space. My thinking is that will then lead to the grand idea of actually doing data processing while you're acquiring the data. That is, it'll change the face of the way we think about doing drone surveys. We're not there. It's still coming. There's still a lot of problems to resolve before then. But the biggest issue, and is really for most of us, is the cost of getting a drone that makes it affordable for us to actually acquire the geophysical data. One that's capable of lifting it, one that's reliable, one that can be a workhorse in terms of day-to-day operations, and one that we can configure with the sensors that we think are the most important for the project. So the U.S. government has their point of view about Chinese-made drones, which has limited some of us from actually working on U.S. military projects or U.S.-owned projects. But there's a lot of use for drone geophysics outside of that, and some of us, me for example, I tend not to worry about U.S. projects or federal projects. I tend to think of work for companies that are more independent of that. mining companies and all.
Okay, I'm going to move on to another question because we have quite a few, and we have quite a few people who'd like to speak. Kian, would you still like to address your question? I think that was that's the farthest back. I think I saw one.
I'm happy to save it till later or tomorrow.
Okay.
Brandon.
Brendan Ray, if you can't speak, maybe your collaborator can read your question because I have lost it in the chat box. I'm sorry. If you can speak, that's fine. Remke, can you find it? I can't seem to find it in the chat.
Yeah, sure.
Thank you.
It's 3 a.m. here, so it's not so easy to speak for everyone. But Brandon asked a question, general questions he wrote. How does the fourth difference magnetic data from drone surveys compare with those expected from fixed wing or heli magnetometer surveys? And how does the sampling frequency of the sensor affect the appearance of such noise levels? Follow up, is it feasible to compare the 4 different noise levels, or would it be better to compare the raw magnetic or unfiltered noise levels instead?
Thank
you. It was Rainer who spoke about this in his presentation.
Yeah, I can answer that one. What difference is the standard of the instrument noise, not necessarily of platform-induced noise. And obviously, yes, the sampling rate is different. So if you have a standard sampling rate traditionally in airborne geophysics was 10 Hertz. So if you have a 20 Hertz system, you should take the 8th difference. There's also some of the fourth difference can be normalized and can be not normalized. Normalizing is basically just dividing by the standard deviation in each window. But it's an instrument noise indicator. It's not an indicator of what noise the entire system, sensor plus platform, is producing.
Yeah.
All right. Did we want to go with a typed question or someone who has their hand raised?
I think we're ready for our next hand raised question.
Okay, that would be Mohammed Haj. I cannot pronounce your last name. I'm very sorry. Haj Haydari?
It is Muhammad Haj Haydari.
Thank you.
Okay. Thank you very much for your good talks and the exciting speech. There was a question I wanted to ask from Joseph, but he was left. And it was about that draped surface matter of the drone flight. Ronald said that we must consider the flight was on a plane and perhaps a horizontal plane. But I think this is a problem that we all will face when we want to invert this data. Do you know any, I can say, commercial or software or applicable code that can consider the draped surface variations within the inversion?
Yeah, I think, well, I've been using Geosoft products for 30 years. I think, yes, you put topography into the top of your 3D or your models in Voxy.
Okay, I don't mean topography. We can use the topography with some kind of constant land clearance, I know. But you know that the land clearance does not mean the draped surface. This aircraft, perhaps, especially about these fixed wings, when they want to become close to these mountains, then they should come up before they can reach the mountains. So they do not obey the topography variations completely, and this makes problem.
Well, I see what you're saying. Yeah.
You need both. in the modeling software. You need the terrain, obviously, and you need the drape surface. And there is Intrepid's 3D geomodeler, for instance, does take both into account. If you do some simple Euler deconvolution or some Phillips method or whatever, then you have to do it basically yourself. You just get you get depth below or model below the flown surface, and that you have to combine with the DTM, and obviously chuck all the models away that are in the air.
And you said that GeoSoft has this ability that can get the drape surface?
I
Perhaps
can
I'm not
comment
aware
on
of it.
that. I can comment on that. This is Elizabeth. It's not GeoSoft anymore. It's Sequent, and the software is Oasis Montage. When you do inversion, 3D inversion, it really inverts relative to your observation datum. So whatever your altitude is, and it doesn't need to be a constant. Then the DEM is used to then locate that below the surface. But really the inversion, it's important that X, Y, and Z of where you're doing the reading is what is used for the inversion.
Okay. Thank you. If you let me, I have another question. I had to ask a question from Ed. It's about the calibration. If I get your point correctly, you must calibrate the data, always the drone data with some kind of land data. And I asked this question, of course, when we want to compare these data together, we must upward continue the land data. But you know that the upward continuation has its own uncertainties. And of course, it is not always possible to compare it with drone data because of this drone drape surface. So how you can actually calibrate this drone data with some kind of land data? Do you consider these uncertainties or not?
Yes, that was just an approximation. I mean, people do this. I just wanted to show that when I took the ground data, which was a better data set because the sensor is constant above the ground and also higher sample density, it happened for that survey when that was put up to about the average survey I was estimating visually. This is all an approximation. When that was put up 1 meter to 3 meters for the average sort of height across the UAV flight over the landfill, it was a pretty good approximation as far as the range of the TMI, but that's just an approximation. If I would fly that another day, it might be 100 off, it might be the range of TMI values, you know, might be more than that, depending on the wander. And it does wander because the satellite constellation's changing. You will get wander in your GNSS positions in the air, in particular. You get it on the ground too. But yeah, that's just an approximation. It's just meant to show that for that survey, when that was upward continued 1 meter, the ground FEM survey was upward continued 1 meter to the UAV FEM survey. It was a pretty close ballpark to the same range of TMI values. So that's, you know, it might have been a good day that day that it was quite close. Other days it might not be so close.
Okay, you mean that if the drone flies close to the surface, then everything is okay. But we have seen a lot of cases that drone cannot be somehow very close to the surface, or we cannot use very long cables due to many problems, as we discussed. And especially, you can consider that we want to use this drone geophysics to explore some kind of ore deposits, some kind of iron veins. We have two problems here. They are too small. We can miss them completely in the drone. And especially when you want to do the calibration, you calibrated the data with some kind of this geomagnetic field. However, we know that these iron deposit minerals always have some kind of remanent magnetization, and so we could not expect that their actual magnetic field components are the same as geomagnetic field because they are not induced magnetic field. Don't you think that it can make a big problem when we want to calibrate the data for such areas?
Well, yes, you try to look for a low gradient area to calibrate your flux gate. That's why they fly at 3,000 meters in practice, the commercial contractors. The thing about a ground calibration is if you can try to emulate a lab calibration, there's hardly any movement of the sensor through the gradient. If it's a fixed centroid, it might be centimeters movement in total that you're getting. So you're minimizing the gradients in the calibration. Yeah, if you're in an ironstone area with magnetites, that's gonna, you know, I've not done that yet, so I can't really talk to that. But if you're in a pretty low gradient area, you can ground calibrate, and it should be a pretty good approximation. I would say more so than flying, trying to do an FOM for a swinging sort of sensor flying around. You're going to introduce external noise into the calibration. You want the calibration to be as clean as possible. So if you do it on the ground using an apparatus, it's like a lab apparatus that only moves that sensor, you know, or even if you have a mobile phone in your hand and you swing it around like that. If you can minimize, see, that's the interesting thing about these calibrations. If you have an invariant fixed value, scalar value, and you can rotate very, very small distances, but a full circle in all directions, a full sphere, you're going to get a valid calibration because there's not much gradient effect in your calibration. I did some work in a rural area too. I didn't show it here. That's for another talk. But your magnetite example, it might be a bit of an issue, but I think if you can get a bit away from the ironstones and get that thing calibrated, you're going to correct for the errors of manufacture in the sensor, and you're also going to correct for maneuvers through a full circle in the Earth's magnetic field. And then you got a good sensor going out to fly, and it's just when it changes direction, it's not going to be much affected. You're not going to get the heading effects you'd get if you did not calibrate that thing. If you don't calibrate it, you're going to get more heading effects, more noise in your data. So I hear your point. I can't say I have experience flying this over a magnetite deposit. I don't, but you should still calibrate that in the field before you fly it. Now, that's for a ground survey, a ground or a isolated slung survey. If you're flying that sensor close to the noise field of your platform, your UAV, then you have to do the full calibration of the flux gate, correction, and compensation for the noise of the platform. If you're within that 3 meter, 4 meter, 2 meter, whatever distance it is, you got to compensate for the noise of the platform. Now, the noise assumption is that it's a fixed object moving through the magnetic field. And now, and if you change that geometry, that's why you don't want a swinging sensor below it to do a figure of merit or a calibration. When it's fixed in the aircraft, you can do that and compensate. Now, if you change the geometry of that aircraft, say you take a motor off, or you take you put something metallic on that, you should recalibrate to compensate that new geometry, that new fixed geometry of your platform. So what's going on here is two things. With a vector magnetometer, you can compensate for the noise on your platform if you fix the thing on your platform. And what I'm saying in my talk today, and I'm sorry the volume was so low, if you get the PowerPoint and have any questions, just email me. My email.
Hi, Ed. I think that we would like to take a look at something else, if that's okay with you. Your contact information is available in the booklet that Lori sent out to everyone. So maybe we can continue this conversation later on in private. I see that Jeff has raised his hand. So Jeff, would you like to unmute yourself and make a comment or ask a question?
Yes, it's just an observation that there is a technique called subaudio magnetotellurics, and it used to be also called magnetometrics. It seems to me that we're talking about just passive magnetic field here at the moment, but if we can get all of the processing done properly, then I see big potential for the SAM technique to be employed using a drone magnetic sensor, and it can be done without having to use a flux gate. You can just use a normal proton magnetometer. So that maybe that's a sort of a bit of a segue into tomorrow's talk when Johannes talks about his semi-EM method. Yeah.
Excellent. I'm glad you brought up tomorrow. So as you all already know, we have another set of talks tomorrow, including EM, and it will be lovely to hear from some new voices and some repeat voices. So we have actually completed our discussion time for today and have moved into the period that we set aside for networking. So if there are those who would like to remain and continue discussing or networking, now's the time to do that. If not, we're going to kind of start to wrap up for today. So I know we had at least one question that was more generally applicable, and I think that we might save that one for tomorrow, and unless people are really gung-ho about answering more questions right now. Otherwise, yes, please take this opportunity to kind of reach out to anyone who you may wish to connect with. Now that you're in the panelists portion, you should have the ability to privately message anyone who is in the panelist space. I know we've had some difficulties with getting the question and answer function to work. It seems it does not work once you're in the panelist space, so I apologize for that confusion from earlier. Hopefully by the end of tomorrow, we'll have kind of gotten our sea legs and it will go more smoothly. But Ron, would you like to make any closing comments for today?
Sure. Morgan, you've done an excellent job of keeping us on track today, and thank you for that. With anybody, if anybody has any experience about putting these kinds of things on, you set a times for people to speak, and you hope that they can fit everything they need to say within that time. I obviously am guilty of not being able to do that very well, but I think today went very excellent, quite well. Tomorrow, we start off with a talk on gamma ray use on drones. I'm actually going to be speaking on some work I've been doing using a shallow-looking drone EM system, which is applicable to environmental work. And Brendan Ray is going to be talking about QA/QC processing. That's a big issue, obviously. And then we'll be finishing up with Callum, who has been a bit of our conscience here over the last few days. And he's going to talk about some of the work he's done for his PhD, where he's examined some of the noise issues with regards to drones. And I hope you all come back and participate, or send your friends to participate. I'm done talking. I thank you all. I'll stay on if anybody wants to network. I think that makes sense. I guess, Lori, is there anything that we've forgotten that we should put up or do?
No, I think we're good. We've had nice discussions today again, so that's wonderful. Yeah, I think we're good.
Well, if anybody can see my video, they see that I actually have a couple drones behind me. I wanted to point out that one of those drones is it's actually probably 6 or 7 years old, and it compared to today's drones, it is antique, and but it's actually the drone that got me into thinking about what was possible with drone geophysics and drone geoscience. We're only touching on the drone geophysics part of it. And I'm just very pleased that you all came to join us and enter in these discussions. All of the speakers have their contact information. We encourage you to reach out to them if you have specific questions. I write a column for the Fast Times called the Geodrone Report. And if you have anything to contribute to that, news about events, information about what you're doing that you would like to share, I would love to have you send it to me, and I'll, if it's appropriate, I'll include it. And then as we go forward, as we started out mentioning that next year, we want to repeat this, actually build the second summit on drone geophysics. And then ultimately our goal is to actually expand it into something a little bit more inclusive, not just a workshop, but something that's maybe more like a conference where we're actually covering a lot of the issues, a lot of the tech that's currently in development and will be developed over the course of the next several years in remote sensing and geophysics basically for geoscientific mapping, whatever the purpose is. So I assume that there's no more interest in, or there's very little interest in the discussion. So we're into the networking game. Thank you all for contributing today, and we'll see you tomorrow.
Yes, thank you again. And just as a quick conclusion, I wanted to say thank you to our sponsors one more time. They were people who believe enough in this to actually put money towards making it possible. So thank you to Geometrics and Sequent and Pegasus Airborne Systems, Hammer Missions, and Southern Geosciences for the contribution. We really value your participation.
Gary has a question. Go ahead, Gary. Please ask your question.
Yeah, thanks. I was wondering if anybody has messed with trying to use the new MFAM technology sensors for magnetics.
What was the question? What was the question again, Gary?
The new MFAM, the new technology that Geometrics has put out, the magnetometer on a chip thing.
Oh yeah, that's the basis of the mag arrow.
It is, okay.
Oh, the mag arrow has two MFAM sensors in it. They're oriented orthogonally. That way they get around having any dead zones. But you can buy the technology. They have a thing called an MFAM development kit, right. And several groups have done that and are flying commercial surveys with that system. They built their own data acquisition system built around it.
And to follow up on, I'm interested in the capability to find pipelines with drones, and how reliable and how reasonable do you think that would be? And well, I'm talking about pipelines that maybe are not out across country, that they might be along roads and so forth. So there definitely would be some flying issues.
I think at least the presentations that I was involved with, the one by Juan Ortega, where there's actually pipeline response in that data. You can see that. In one of the data sets I put up, there's a pipeline response, a couple of them, and it's in the data. And also I've got a really good example of actually not only with the MFAM, with the mag arrow of mapping the location of the pipeline, which is the magnetic response, but because it samples so fast, it actually will measure or detect the EM field that results from the cathodic protection.
Sure.
And I actually have a really nice example of that. I'll be happy to send that to you, Gary.
Yeah, I'd love to see it. My question is more along the lines, can we actually fly surveys where I might need surveys done? I mean, we've been doing magnetics for 100 years. I know we can find pipes with magnetics. That's really not the issue. The issue is, can you fly low enough and slow enough around roads and places where there are people? I don't know the rules very well yet, and I'm just wondering if that is an insurmountable hurdle.
Oh, definitely not insurmountable. And in fact, if I figure out how to operate this this video editing software tomorrow, I'll show a little video of us flying this Gem 2 system at about 1.5 meters above the terrain. I don't want to give away all of that. I'm going to show it tomorrow, but one of the things I've been pursuing is actually being able to fly true terrain following, and I recently upgraded my M600 with a radar altimeter, and that allows that. I literally did that last week, and we flew twice, and actually got a reasonable field trial in on Friday, and then next week I'll be out flying again, trying to sort out what the issues are, trying to make it a functional system. But that, whether I'm flying the EM system or I'm flying a magnetometer or any other sensor, the technology for flying sensors at that low of altitude, ultra low altitudes, is coming to the market, and it's being made available. And anybody with the right amount of money can actually get it. So.
Okay, well, I'm looking for the capability to do that, but I want to get a service provider to help me start it. So anybody that can hear me, please reach out, Lori. It's okay to give them my email, and I'd like to talk more about doing this.
I will reach out to you. I do services, so, and I provide services. So
I'm going to politely request that everyone who wishes to do that does that privately, only out of respect for the sponsors who have actually paid to have their names involved in this.
Sure. And by the way, I plan to reach out to all the sponsors.
Wonderful. Thank you, Gary.
Can I just, this is Keen, can I just add a quick comment onto Gary's questions?
Yes.
So flying a lot of different places that I've been, part of the question, Ron talked about the technical aspects of it, but part of it that you were asking about, I think also is the regulatory aspect from FAA rules.
Right.
And so it really varies depending on your location. So, I fly surveys that cross roads frequently, but it depends on how busy the roads are, whether or not we think that interferes with, sort of whether or not that's in compliance with FAA rules. But when you do want to deviate from those, you can apply for waivers. So companies who are doing a lot of more geophysics, a lot more drone work, are often applying for waivers from certain specific rules. So there are ways to work within the regulatory process, but go beyond what the basic, what's called Part 107 allows.
Cool, thank you.
Yeah, thanks, Kian, for bringing that up. Really, there is some controversy in the drone business about how low you can fly. That's sort of a matter of interpretation at this point in some cases, most cases. I think Texas, I was going to try to make a joke out of that because, but I'll avoid that. From a technical point of view, there's no problem flying. Well, we're solving the problem of flying at very close to the ground surface. Detecting pipelines is one of the things that people want to do. Archaeology, there's a big interest in using drones for doing archaeological studies. The big interest in UXO, as you probably have seen. What I see as the future is that not only will we be doing geophysical measurements on the same pass, we'll be also doing some sort of remote sensing measurement, whether it's thermal imaging or some sort of hyperspectral, or whether it's just color photography, or even potentially even a LiDAR survey. It's almost unlimited. It's really limited to two things. One is your imagination, and secondly, I guess three things: technical feasibility, whether it makes sense or not, whether we have the tech to do it, And then thirdly, it's the amount of money that the problem demands or commands. Everything is somewhat driven by what we can get for the data that we're acquiring. An observation that I'll make is that very often the aviation guys tend to think of the aviation as being the center of the universe when it comes to drones. And from the data guy point of view, which I'm clearly one of, the aviation is just sort of the process that you need to have in place to actually acquire the data. And the advantage of using drones is not necessarily because they're cool, although I do think they're kind of cool. It's really about the automation of it. It's really about being able to acquire data sets, large volumes of data sets, eventually very large volumes of data sets, pretty much automatically without human intervention. That's you can point to a number of other industries and see where that's really been a lot of the driving force in the development of the industry is the data part of it. And so, although we haven't touched on much of that, what to do with the data afterwards, we're kind of trying to solve the problems of getting good data. But eventually we'll be having discussions about how do we, apply our analytical techniques to really pulling the information out of a data, and data volumes that are going to be comprised of multiple data types. And eventually that will be, whether it's GPR or MAG or EM or hyperspectral, whatever, eventually the drones will take somewhat of a second seat to the discussions about and efforts to actually improve our ability to extract information out of the data. But that's not where we're at today. Today, we're just trying to solve the basic problems of getting good data.
All right. So I have a question.
All right.
I may have missed this, but is anybody experimenting with laser altimetry, with magnetic surveys, with the laser in the loop for the flight software, so that the UAV actually reacts to the real-time information that it's getting, or the near real-time information that it's getting?
In maintaining the altitude?
Yeah, exactly. So that it could actually maintain whatever elevation was.
Yeah. The knowledge I have is that the guys at SPH Engineering have their true terrain following module for their UGCS, which stands for Universal Ground Control Software, is compatible with laser altimeters as well as a radar altimeter. And they have 3 that they list that's compatible with. I actually upgraded with a radar altimeter because according to their work, their field trials, that's been much more effective when you are closer to the ground. And but the laser altimeters have a role to play when you're flying at higher elevations. So those are the ones I know about. I know about Skyfront, which has got the Perimeter X4 and X8, and we did a field trial in August of the Mag Arrow, and where we flew it using well, he initially had laser altimeters. It was mounted on the aircraft, but we ended up doing our field trial with the RTK GPS, which seems to have worked quite well. And they tended to want to go with that rather than use the laser altimeter. This kind of leads into the topic of discussion about when do you decide to use, whether it's laser or radar or RTK or whatever. And I have my ideas, but I don't know. What do you think, Jeff?
Yeah, I don't think we're getting great information from the vertical GPS. Is that what you're talking about? The vertical GPS?
Yeah, I don't know what the resolution of the art. Certainly, the standard GPS isn't giving us very good resolution.
Even the good ones, I think, aren't great if we're doing, you know, the sort of close to the ground stuff. You know, of course, as we go higher, it matters less. But you know, if we want to be 10, 15, 20 meters from the ground, I think we should go with some kind of altimeter. And I hadn't thought about radar, and if those are more accurate close to the ground, that's a good idea.
Right. What you have is when you're on the ground, I see a couple problems. One is you've got the vegetation issue of, you know, basically the ground cover, and that can actually impact the responsiveness of the altimeter. But I see that as just a matter of writing an algorithm that lets you control what it is thought that it should be from what you're actually measuring, and then controlling the aircraft accordingly.
There's just some engineering issues in there.
Yeah, it's more of an engineering issue. Yeah, it really is an engineering issue, and I'm sure that there are some folks that are working on it. Really, the level of focus comes from where you want to apply the technology. That is the geophysical technology. Certainly the GPR, one of the things about the GPR stuff is that you've got to fly that pretty damn low. You have no alternative in terms of when it comes to dealing with the data. With MAG, you maybe don't have to be so low. You know, you can. It depends on what you're doing, though. If you're looking for UXO, you got to fly that thing at centimeters scale, just centimeters off the thing.
Yeah.
So.
Yeah. Oh, totally unrelated question. I saw somebody with a chart, but is there a general sense of the cost per line mile on the UAV? I sort of had a rule to back of the envelope calculation, but just interested in what current, you know, contracting and companies are looking at these days.
In my work, I really hate to try to cost it per a line mile. I'll cost it per an average coverage area, you know,
right,
per acre. That
it depends on your line spacing, though, right?
It absolutely does. And so when you go to cost per line mile, I just proposed on a middle survey where I came out to being about $100 a line mile.
Okay, that's less than what I was thinking. I had it about twice that.
Yeah,
so it sounds like it's come down a little bit.
That or I'm too cheap.
Right. Well, the only reason I ask about that is because I get questions of, well, how does this compare with costing of a manned survey? And of course, they're kind of two different things, but you know, that's kind of a question that I often get. And you know, man, you do by line miles, so that just seems like a reasonable. I don't know how reasonable it is, but an easy yardstick to compare.
Yeah,
it's not really reasonable because they're kind of different.
Hey, Jeff, I would throw out an additional consideration to what Ron mentioned and what you're mentioning. And with the drone surveys, one of the real issues is the terrain and the conditions and the line of sight.
Right.
So where, you know, in a plane, you're able to get, okay, I'm flying over this, and so it's all standard. It could be very different site by site in terms of how far you can actually fly, depending on how, like, the distance and what the obstacles are for you to be able to actually maintain line of sight. So, you know, and the other thing is it depends on sort of how noisy in terms of communications, your quality of GPS. So I've gone to sites where, you know, I thought I was going to fly from 2 locations and get, you know, each end and hit the middle, and that was it. And I ended up having to move at like 1/4 to 1/2 mile intervals. And so the actual field conditions, you know, completely overruled sort of the original plan, and that the timing then that was involved was radically different. Whereas if I was just flying and didn't have to worry about that in a plane, it would have been, you know, those 2 things wouldn't have made a single difference. So I think you're potentially going to run into some issues with the drones that make it harder for certain standardized.
Yeah, no, that's a good point. Like I said, they are kind of 2 different things. I mean, you either want to do a manned survey or a drone survey, but you know, one's not going to replace the other.
Yeah, go ahead. Ask your question.
Okay. I think the method of data fusion was really absent today. It was really necessary to see that if we fuse this data with drone, with other kinds of data, for example, with land data, can it somehow give us some more accurate data or not? You know that we use drones because in many cases we cannot actually do the land measurements. It is not possible, as we mentioned today, but it is possible for many cases that we have problem with drones. For example, some of the talks was about that we have problem with leveling of the data. Perhaps we miss some of the data. And I think in these cases, we need to do some, at least at some limited number of points, some land measurements, and then fuse this data with the drone data. I want to know that if any of you have some experience with data fusion, have you tried to fuse this data with some other kind of data or not, even with satellite data?
I think the answer is yes, but not specifically with the purpose of data fusion. Most of us that are doing site characterization, whether in the environmental world, we're oftentimes we're using multiple data types, and sometimes those data are actually acquired with the drone. But I think it's an early days type thing, Mohammed. It's something that I'm sure a few people are doing, but not many, because well, I can't say not many, but a few. And it's growing. It should be. I mean, I think that we should be looking at combining MAG with or EM or GPR with other data types.
I don't mean data types. I mean the same data type what we measure it from different conditions. For example, with airborne data, with land data, and at the same time, for example, if we have some problems with the drone data, we have problems with leveling them. We have problems if we want to somehow seek some continuous data. You see that we have always problem with these continuities. I forgot his name, but one of the speakers today were talking about that we have this micro leveling problems, and we could see some stripes between the drone flight lines and so on. I told him that we could, for example, along these stripes, we do some kinds of land measurements, and then we can fuse this data. We can then somehow upward continue the land measurements in few points. For example, with not, I can say with larger spacings. And then we can combine it or fuse it with this drone data, and we can solve the problems that we have today with drone data. This is what I mean, not combining EM and MAG data.
Okay.
And I want to see that if somebody has done that or not.
Yeah, I can speak to that. So 2 years ago, I flew a survey where we did over mineral exploration site. We did an entire ground survey. We did 3 levels of UAV borne, and then we also had very high resolution 85-meter airborne and compared them all between that. So wrote a paper on it, put it in the description there if you want to look into that.
Thank you.
No worries.
And another question I have, we talked a lot today about the calibration, and I give a suggestion to Johannes, and he actually verified my suggestion that we could simply use some other kinds of magnetometers, for example, a proton magnetometers together with a vertical flex gate with a vector flex gate magnetometer. For example, we can calculate the TMI with flex gate, and we have the TMI from the proton magnetometers. If they match together very well, it means that we calibrate well. And it is not necessary to go to these kinds of very, I can say, very difficult calculations for calibrations. It is much easier, isn't it?
Yeah, it's it'll probably be something to discuss more tomorrow once I give a little bit more background into what the research I've done on this subject has been. So I'd be interested to hear kind of what everyone's thoughts are with this tomorrow in the discussion, because I kind of give a very good characterization of what these signals are, where they come from, and what we need to be able to do to get good data from it. So I think that'll be more of a discussion for tomorrow. But as you said, one of the ways that people have been thinking of being able to do this is, say, put a flex gate magnetometer hard mounted on the drone and then be able to correct the signal based off that. And it's one of the possible methods. And I think this is where there's more research that needs to be done to be able to do it. But look forward to that conversation.
Okay, thank you.
All right, I see someone has their hand up.
It's me.
Go ahead.
I have my hand up because we had one more question that came in through the chat, and I wanted to make sure it got addressed. So realistically, I think this is going to be our last question. And the question is, how bad can be an area with very dense vegetation like tall pines for a mag survey? So if anyone wants to kind of address the vegetation question in more detail.
So would you repeat the question, Morgan, please?
I think this person is asking how the vegetation impacts mag surveys. So it sounds like they're in a very, or considering a very densely vegetated area, specifically with tall pines.
Okay. Oh, trees are vertical structures. We try to avoid them. We don't like running into them. They're not a good thing for our instrumentation or our drones. So we tend to fly above the tree canopy. I've done that, and the only way that I could do that successfully was using a boom lift to lift my pilot up so he could actually maintain visual line of sight with the aircraft. It was positioning the pilot was one of the challenges for that particular project, and I anticipate that. Fortunately, it was in an area that's kind of like Canada, at least Eastern Canada, where it's relatively flat, reasonably tall trees, and so we were able to move around. It was a forested area that was being logged off, so there were open spots that we could actually drive to and put the boom lift up and get the pilot up in the air. That's the only way that I know how to do it effectively. Caleb, you must have worked in highly forested areas.
Yeah, I've worked in the Boreal quite a bit, walking through it and flying through it and all sorts of stuff. Typically, what the best thing that you'd want to do is either go fly a photogrammetry survey beforehand to get a really good idea where the tree canopy is, until we get systems where you can literally fly, meters above the tree canopy with accuracy, which, I mean, I don't think I've seen anyone do that yet. It was just you had to guess what your tallest tree was and try and avoid it in the area and do it. Scissor lift, I mean, is a very common way that people do this to be able to maintain line of sight. Otherwise, you're trying to get up on the highest hill that you have, sort of thing. But it's a consideration in these forested areas, which is where most of my work has been, up in mineral exploration in Northern Ontario.
All right. Well, thank you for answering that last question. And with that, I think we're going to go ahead and conclude this session for today. I hope to see you all tomorrow, and for those of you headed to bed, have a good night.
Yeah. Or getting up for a new day. Have a good day.